You have heard this phrase before, 10 times faster than light. It appears in headlines with regularity now, attached to words like breakthrough and discovery and scientists reveal. It sounds like progress. It sounds like we're approaching something that was once forbidden, as though the universe is slowly yielding to human ambition and the barriers that seemed absolute are beginning to crack. But this is not what is happening. What is happening is more subtle, more interesting, and in some ways more unsettling than the promise of faster-than-light travel. What is happening is that physicists have found ways to describe mathematically how space-time could be manipulated to produce motion that appears to exceed the speed of light, while technically not violating the laws that govern our universe. They have written equations that work on paper. They have reduced the theoretical energy requirements from impossible to merely absurd. They have shown that the rules, as we understand them, contain a narrow corridor through which something resembling faster-than-light travel might squeeze if conditions that do not exist in nature could somehow be created and sustained. This is not the same as being able to do it. When you read that scientists have revealed a method to travel 10 times faster than light, what you are reading is a statement about mathematics, not engineering. You're reading about a solution to Einstein's field equations that permits a specific configuration of space-time, one that has never been observed and may never be possible to create. You're reading about the difference between what the universe allows in principle and what it allows in practice, and that difference is so vast that it makes the distance between stars seem trivial by comparison. This video is not about whether we will one day travel faster than light. It is about what that phrase actually means when you examine it closely. It is about understanding why light moves at the speed it does, why that speed represents a boundary woven into the structure of reality itself, and why even the theoretical methods designed to circumvent that boundary do not escape it so much as redefine what motion means. It is about the difference between moving through space and moving space itself, between velocity and geometry, between what seems possible when you solve an equation and what remains impossible when you try to build something real. The speed of light is not arbitrary. It is not a speed limit imposed by some cosmic traffic law that clever beings might one day learn to evade. It is a property of space-time, a feature of how reality is assembled at its most fundamental level. When we talk about exceeding it, we are not talking about going faster. We are talking about restructuring the space through which motion occurs, warping the fabric of the universe so severely that the normal rules about distance and time stop applying in the way they usually do. And even this, even the careful, theoretical framework that describes how it might be done, requires things that probably do not exist. This is not a story about a breakthrough. It is a story about distance and about the universe's relationship with distance. It is about how far light can travel in a year, and how far human beings have travelled in their entire history, and what it means that those two numbers are separated by a gulf so extreme that no amount of engineering or fuel or willpower can bridge it using the methods we understand. It is about why physicists began looking for loopholes in the structure of space-time itself, and what they found when they did, and why even those loopholes remain closed in every practical sense. You think you understand what it means to go fast. You have been in cars and trains and airplanes. You have felt acceleration press you into your seat. You have watched landscapes blur past windows and felt the sensation of covering distance quickly. But the speed of light is not a faster version of that experience. It is a different thing entirely, a speed so extreme that it stops being about motion in any intuitive sense and becomes about the structure of causality, about what it means for one event to influence another, about the order in which things happen and whether that order can be preserved. When scientists describe a method to travel 10 times faster than light, they are describing a way to break causality itself, to move through the universe in a manner that makes the concept of before and after ambiguous. They are not simply proposing a faster engine, they are proposing a reconfiguration of the relationship between space and time, one that comes with implications so strange that they border on paradox. And yet, the mathematics allows it. Under extremely specific conditions, with resources that do not exist, and energy densities that have never been measured, the equations describe a way forward, not a way to go faster than light, but a way to compress the space in front of you and expand the space behind you so that you arrive somewhere distant without ever moving through the space between at a speed that exceeds light. The distinction matters. It matters more than anything else in this entire discussion. This video will take you through that distinction step by step. It will begin where all understanding of speed must begin, with the human experience of motion and distance. It will expand slowly outward, first to the scale of planets, then to stars, then to the vast empty regions between stars where light itself takes years to cross. It will explain why light moves at the speed it does, and why nothing with mass can match it. It will show you the wall that physics has built into reality, and then it will show you the one narrow theoretical crack in that wall, the geometric loophole that might, under impossible conditions, allow something resembling faster-than-light travel. And then it will show you why, even with that loophole, the universe remains as large and as distant as it has always been. By the end, you will understand what scientists mean when they say they have found a method to travel faster than light. You will understand why it does not mean what the headlines suggest, and you will understand something deeper about the nature of distance itself, about why the universe is built the way it is, and about the quiet, absolute limits that govern all motion, all travel, and all human ambition to reach beyond the small corner of space we were born into. This is not a story about speed. It is a story about the universe, and about the difference between what we can imagine and what we can do. You know what speed is because you have experienced it your entire life. Speed is the feeling of a car accelerating onto a highway, the way the engine noise rises and the scenery begins to slide past the windows faster and faster until the individual trees blur into a continuous streak of green. Speed is the difference between walking and running, between a bicycle and a motorcycle, between standing still and covering ground. It is measured in simple terms: miles per hour, kilometers per hour, feet per second. These are numbers you can feel in your body. When you drive at 60 miles per hour, you are covering 60 miles in 1 hour. If you maintain that speed, you will travel 120 miles in 2 hours. The mathematics is straightforward. The experience is intuitive. You understand what it means to go twice as fast because you have been in vehicles that go twice as fast. You understand what it means to cover distance quickly because you have covered distance quickly. Speed, at the human scale, is one of the most accessible concepts in physics. It is simply distance divided by time. But even at this scale, even within the range of speeds you encounter in daily life, there are hints that speed is more complicated than it appears. When you accelerate, you feel a force pushing you backward into your seat. The faster you accelerate, the stronger that force becomes. This is not arbitrary. It is a consequence of inertia, the tendency of objects to resist changes in motion. Your body wants to remain at the speed it was travelling. When the car accelerates, the seat must push against you to change your velocity, and you experience that push as a force. The sensation is real, the force is real, and the energy required to produce that force increases the faster you go. At highway speeds, this is barely noticeable. Accelerating from 0 to 60 miles per hour requires a certain amount of energy, and accelerating from 60 to 120 requires more, but not drastically more. The relationship is not linear, but it is manageable. Cars are designed to handle these accelerations. Engines are built to provide the necessary force. Fuel contains enough chemical energy to push a vehicle up to speeds that feel fast by human standards. The system works because the speeds involved are small compared to the fundamental limits of physics. Now consider a commercial airliner. A Boeing 747 cruises at approximately 570 miles per hour. This is nearly 10 times faster than highway driving. At this speed, you are covering the distance from New York to Los Angeles in less than 5 hours, a journey that would take more than 40 hours of continuous driving. The airplane achieves this speed by burning thousands of gallons of fuel, by generating enormous thrust through its engines, and by operating at an altitude where air resistance is reduced. The energy cost is significant. The engineering required is complex, but the speed is still within the realm of human intuition. You can imagine going 10 times faster than a car. You can picture what it would feel like, even if you have never experienced it directly. Fighter jets go faster still. The fastest military aircraft can exceed 2,000 miles per hour, roughly 3 times the speed of sound. At this velocity, you're moving so quickly that the air itself cannot get out of the way fast enough. It compresses in front of the aircraft, creating shock waves that propagate outward as sonic booms. The forces involved are extreme. The materials must withstand temperatures high enough to melt conventional metals. The fuel consumption is staggering. And yet, even at Mach 3, even at 3 times the speed of sound, you're still moving slowly compared to the scale of the solar system. You're still bound by the physics of momentum and energy in a way that feels comprehensible. The fastest human-made object ever built is the Parker Solar Probe, a spacecraft designed to study the Sun by flying closer to it than any previous mission. At its maximum velocity, the Parker Solar Probe reaches approximately 430,000 miles per hour. This is fast enough to travel from Earth to the Moon in less than 30 minutes. It is fast enough to cross the United States in less than 7 seconds. It is more than 200 times faster than a fighter jet and nearly 1,000 times faster than a car on the highway. The probe achieves this speed by falling toward the Sun, using the Sun's immense gravitational pull to accelerate to velocities that no chemical rocket could ever produce. And yet, even at 430,000 miles per hour, even at a speed so extreme that it exceeds anything else humans have ever created, the Parker Solar Probe is moving at less than 1/15 of 1% of the speed of light. If you pointed the probe at the nearest star beyond our Sun, a star called Proxima Centauri located just over 4 light-years away, it would take more than 6,000 years to reach it. 6,000 years. That is longer than recorded human history. That is longer than the entire span of human civilization, from the first cities to the present day. And that is travelling at the fastest speed humanity has ever achieved. This is where intuition begins to fail. You can imagine going faster than a car, you can imagine going faster than an airplane, you can even imagine, with some effort, going as fast as the Parker Solar Probe, though the number becomes abstract and difficult to hold in your mind. But when you try to imagine going fast enough to reach another star in a human lifetime, the numbers stop making sense. The speeds required are so far beyond anything you have experienced, so far beyond anything that exists in your frame of reference, that they cease to feel like speeds at all. They become abstract values, figures on a page, disconnected from the physical sensation of motion. And this is still only the beginning. The speed of light is not twice as fast as the Parker Solar Probe, or 10 times as fast, or even 100 times as fast. Light moves at approximately 670 million miles per hour. To put that in perspective, light can travel around the entire circumference of Earth more than 7 times in a single second. It can reach the Moon in 1.3 seconds. It can travel from the Sun to Earth in 8 minutes and 20 seconds. And it can cross the 4 light-years to Proxima Centauri in exactly 4 years, because that is what a light-year measures, the distance light travels in 1 year. The difference between the fastest speed humans have achieved and the speed of light is not a gap that can be closed with better engineering or more powerful engines. It is not a matter of building a bigger rocket or finding a more efficient fuel. The Parker Solar Probe, travelling at 430,000 miles per hour, is moving at approximately 0.064% of the speed of light. To reach just 1% of the speed of light would require increasing the probe's velocity by more than 15 times. To reach 10% of light speed would require increasing it by more than 150 times. And to reach the speed of light itself would require infinite energy, for reasons that will become clear in the chapters ahead. This is the ground truth. This is the baseline against which all discussions of faster-than-light travel must be measured. Human beings, with all of our technology and ambition and resourcefulness, have managed to accelerate a small spacecraft to less than 1/10 of 1% of the speed of light. We have done this by using gravity itself, by falling toward the Sun and stealing momentum from the most massive object in our solar system. And even at that speed, the nearest stars remain thousands of years away. The galaxy remains inaccessible. The universe, in any practical sense, remains closed to us. When scientists talk about travelling 10 times faster than light, they are talking about speeds that are not just beyond current technology, but beyond any technology that operates on principles we currently understand. They're talking about moving at 6,700,000,000 miles per hour. They are talking about crossing the distance to Proxima Centauri in less than 5 months. They are talking about reaching the centre of our galaxy, 26,000 light-years away, in 2,600 years instead of 26,000. These numbers sound impressive. They sound like progress. But they are still measured against a universe so vast that even 10 times the speed of light is barely enough to make it navigable. Before you can understand how faster-than-light travel might theoretically be possible, you must first understand why it is impossible. You must understand what light is, why it moves at the speed it does, and why that speed represents an absolute boundary that cannot be crossed by any object with mass. You must understand that the speed of light is not a speed limit in the conventional sense, not a rule that could be broken with enough force or cleverness, but a property of space-time itself, woven into the fabric of reality at a level so fundamental that violating it would mean violating causality, violating the sequence of cause and effect that makes the universe comprehensible. This chapter has established the scale. It has shown you how fast humans can actually go and how slow that is compared to light. The next chapter will show you what light is and why its speed is special. Light is not like other things that move. When you throw a ball, its speed depends on how hard you throw it. When you drive a car, its speed depends on how much pressure you apply to the accelerator. When a rocket launches, its speed depends on how much fuel it burns and how efficiently that fuel is converted into thrust. In every case, speed is a variable. It can be increased or decreased. It can be measured relative to different observers. If you're standing on the side of a road and a car passes you at 60 miles per hour, that is the car's speed relative to you. But if you are in another car travelling at 40 miles per hour in the same direction, the first car appears to be moving at only 20 miles per hour relative to you. Speed, in the ordinary sense, is relative. It depends on perspective. Light does not work this way. Light moves at the same speed for every observer, regardless of how fast they are moving or in what direction. If you're standing still and you measure the speed of a beam of light, you will find that it travels at approximately 186,000 miles per second. If you are in a spacecraft moving at half the speed of light and you measure the speed of that same beam, you will still find that it travels at 186,000 miles per second relative to you. The light does not appear to be moving faster or slower depending on your motion. It always moves at exactly the same speed. This is not intuitive, it seems impossible. But it is one of the most thoroughly verified facts in all of physics. This constancy, this invariance of the speed of light, is the foundation upon which the entire structure of modern physics is built. It was discovered in the late 19th century through a series of experiments designed to measure the motion of Earth through what was believed to be a luminiferous ether, a medium that permeated all of space and through which light waves propagated, much like sound waves propagate through air. The experiments, most famously the Michelson-Morley experiment of 1887, were designed to detect Earth's motion through this ether by measuring tiny differences in the speed of light depending on the direction of Earth's movement. The results were unambiguous. There was no difference. Light moved at the same speed in all directions regardless of Earth's motion. The ether did not exist. And light, it turned out, did not need a medium to propagate. It moved through empty space at a constant speed that did not depend on the motion of the source or the observer. This finding was so strange, so contrary to everyday experience, that it took nearly 2 decades for physicists to fully understand its implications. The resolution came in 1905, when Albert Einstein published his theory of special relativity. Einstein proposed that the speed of light was not just constant by coincidence or measurement error, but constant as a fundamental law of nature. He built an entire theory around this single principle, and that theory predicted consequences so bizarre that even Einstein initially doubted whether they could be real. Time, according to special relativity, is not absolute. It passes at different rates depending on how fast you're moving. Space is not absolute either. Distances contract in the direction of motion. Mass increases with velocity, and nothing with mass can ever reach the speed of light, no matter how much energy you apply. These predictions have been confirmed thousands of times in laboratories and observations around the world. Particles accelerated to speeds approaching light in particle colliders behave exactly as special relativity predicts. Their masses increase, their internal clocks slow down. Muons, subatomic particles that normally decay in microseconds, live significantly longer when travelling at near-light speeds because time passes more slowly for them. GPS satellites orbiting Earth must account for relativistic time dilation, or their positioning data would drift by miles every day. The effects are real, they are measurable, and they all stem from the single fact that light moves at a constant speed for all observers. But why does light move at this particular speed? Why 186,000 miles per second and not some other value? The answer lies in the structure of spacetime itself. Space and time are not separate things. They are aspects of a single four-dimensional fabric, a unified entity that Einstein called spacetime. Events do not occur in space and then in time. They occur in spacetime at specific coordinates that combine location and moment into a single point. And the geometry of spacetime, the way distances and durations are measured and related to one another, is governed by a fundamental constant that appears in the equations describing electromagnetic fields, in the equations describing gravity, in the equations describing the behavior of matter at the quantum level. That constant is the speed of light. Light moves at the speed it does because that speed is built into the structure of spacetime. It is the maximum speed at which any information, any influence, any causal connection can propagate from one point to another. When you flip a light switch, the electromagnetic signal does not reach the bulb instantly. It travels at the speed of light through the wire. When the sun suddenly disappeared, we would not know it for 8 minutes and 20 seconds, because that is how long it takes light to travel from the sun to Earth. Cause and effect are limited by the speed of light. The universe has a speed limit not because of friction or resistance or any physical barrier, but because causality itself cannot propagate faster than light without breaking the logical structure of time. This is why nothing with mass can reach the speed of light. As an object accelerates, its mass effectively increases from the perspective of an outside observer. The faster it goes, the more massive it becomes, and the more energy is required to accelerate it further. At 90% of the speed of light, an object's mass has more than doubled. At 99% of the speed of light, its mass has increased by a factor of 7. At 99.9%, the factor is 22. As the object's speed approaches the speed of light, its mass approaches infinity, and the energy required to accelerate it further also approaches infinity. You cannot reach infinity. You cannot supply infinite energy. The speed of light is not a barrier you can push through with enough force. It is an asymptote, a limit that can be approached but never reached. Photons, the particles of light itself, do not have this problem because they have no mass. A photon at rest would have zero energy, but photons are never at rest. They are created moving at the speed of light, and they remain at that speed until they are absorbed. They do not accelerate. They do not slow down. They simply exist at light speed, because that is the only speed at which a massless particle can exist. Anything with mass must move slower than light. Anything without mass must move at exactly the speed of light. There is no in-between. This creates a profound asymmetry in the universe. Information can travel at light speed through electromagnetic radiation, through gravitational waves, through any massless field. But matter, anything with mass, anything that can carry structure or complexity or life, is forever confined to speeds below light. The gap between these two regimes is absolute. You can accelerate a particle to 99.9999% of the speed of light, so close that the difference is unmeasurable by most instruments, but you can never close that final gap. You can never reach 100%. The universe does not permit it. And yet, when physicists say they have found a method to travel 10 times faster than light, they are not proposing a way to accelerate matter to speeds beyond light. That remains impossible. What they are proposing is something more subtle, something that exploits the fact that spacetime itself is not a fixed stage but a dynamic fabric that can be warped, bent, stretched, and compressed. The speed of light is constant within spacetime, but spacetime itself can move. Space can expand faster than light, space can contract, and if you can manipulate the shape of space in the right way, you can create a configuration where an object remains stationary, relative to the space immediately around it, while that space itself moves, carrying the object along with it at speeds that appear from the outside to exceed the speed of light. This is not science fiction. This is a consequence of general relativity, Einstein's theory of gravity and spacetime curvature. General relativity allows for solutions where space itself expands or contracts at arbitrary rates. The expansion of the universe is one such solution. The space between galaxies is expanding, and galaxies that are sufficiently far away are receding from us at speeds greater than light, not because they are moving through space faster than light, but because the space between us and them is expanding. The galaxies themselves are not violating the speed limit. They are simply being carried along by the expansion of space, and there is no law that prevents space from expanding faster than light. If space can expand faster than light, then in principle space can also be made to contract faster than light. And if you could create a region of space-time where space contracts in front of you and expands behind you, you could theoretically ride that wave of space-time curvature, remaining stationary relative to the space around you while covering vast distances in a short time. This is the core idea behind the Alcubierre warp drive, the most famous theoretical method for faster-than-light travel. It does not involve moving through space at speeds exceeding light. It involves moving space itself, warping the geometry of space-time so that the effective distance between 2 points becomes shorter than it would be in flat, unwarped space. But there is a cost. There is always a cost. General relativity permits these solutions mathematically, but the equations also reveal what would be required to create them. The energy densities involved are not merely large, they are exotic, they are negative. They require forms of matter or energy that have never been observed in nature, that may not exist at all, and that would violate principles of physics that have held true in every experiment ever conducted. The warp drive is allowed by the equations, but it is not allowed by reality, as we currently understand it. This is the breaking point. This is where the possibility encoded in mathematics diverges from the possibility of actual construction. The speed of light remains unbroken, the barrier remains intact, and the methods proposed to circumvent it remain, at best, theoretical curiosities, solutions to equations that describe worlds we cannot build. To understand what travelling faster than light would actually mean, you must first understand what light itself experiences when it travels. This requires a shift in perspective, a willingness to abandon the intuitive sense of time and distance that governs human life and adopt a viewpoint that feels alien and contradictory. From our perspective, light takes time to travel. A beam of light emitted from the sun takes 8 minutes and 20 seconds to reach Earth. Light from the nearest star takes 4 years. Light from distant galaxies takes billions of years, travelling across unfathomable distances before finally arriving at our telescopes. We measure these journeys in time because time is how we experience duration, how we quantify the interval between one event and another. But from the perspective of light itself, no time passes at all. A photon emitted from the surface of the sun and absorbed by your eye 8 minutes later does not experience those 8 minutes. From the photon's frame of reference, if such a frame could be meaningfully defined, its emission and absorption occur at the same instant. The journey that takes 8 minutes from our perspective takes 0 time from the photon's perspective. This is not a metaphor. This is a direct consequence of special relativity. As an object approaches the speed of light, time dilation becomes more extreme. At the speed of light, time dilation becomes infinite. Time stops. Or more precisely, the passage of time becomes undefined, compressed to a singularity where all moments along the photon's path exist simultaneously. Distance undergoes a similar transformation. From our perspective, the photon travels 93 million miles from the Sun to Earth, but from the photon's perspective, that distance contracts to 0. Length contraction, like time dilation, becomes infinite at the speed of light. The space between the Sun and Earth, from the photon's viewpoint, does not exist. The photon is emitted and absorbed at the same point in space-time. There is no journey, there is no duration, there is only a single event, an instantaneous connection between emission and absorption that spans what we perceive as 8 minutes and 93 million miles. This creates a profound conceptual problem when trying to imagine what faster-than-light travel would feel like. If you could somehow accelerate to the speed of light, time would stop for you. The universe outside your ship would age infinitely fast. You would reach your destination instantaneously from your perspective, but an infinite amount of time would have passed in the outside universe. You could not reach the speed of light and then continue accelerating beyond it, because there is no subjective time in which to experience that acceleration. The very concept of travelling at light speed breaks down when examined from the traveller's perspective. You cannot move through time if time does not pass for you. And yet the universe is filled with things that move at the speed of light. Every photon, every gravitational wave, every massless particle crosses vast distances without experiencing the passage of time or distance. The light reaching us now from distant galaxies was emitted billions of years ago from our perspective, but from the photon's perspective, its entire journey was instantaneous. The structure of space-time creates a fundamental divide between observers moving slower than light, who experience time and distance in the normal way, and entities moving at light speed, for whom time and distance collapse into a single point. Now consider what it would mean to travel faster than light. If at light speed time stops and distance vanishes, what happens beyond that boundary? The mathematics of special relativity does not permit this scenario. If you try to solve the equations for an object moving faster than light, you encounter imaginary numbers in places where physical quantities should appear. Time becomes imaginary. Length becomes imaginary. Mass becomes imaginary. These are not solutions that describe anything real. They are mathematical artifacts that indicate you have violated the assumptions under which the equations were derived. Special relativity does not describe faster-than-light motion, because faster-than-light motion is not a thing that can exist within the framework of special relativity. But ignore the mathematics for a moment and try to imagine it anyway. Imagine you are travelling at twice the speed of light. You leave Earth and head toward Proxima Centauri 4 light-years away. At twice light speed you would arrive in 2 years from Earth's perspective. But from your perspective, what would you experience? If time stops at light speed, what does time do beyond light speed? Does it reverse? Do you experience the journey backward, arriving before you left? Do you age negatively? Do you observe the universe running in reverse outside your window? These questions do not have answers because they are based on a premise that violates the structure of causality. Faster-than-light travel does not simply mean arriving at your destination more quickly. It means violating the sequence of cause and effect. In special relativity, 2 events separated in space can have different orderings depending on the observer's motion, but only if the events are far enough apart that light could not travel between them. If event A and event B are separated by a distance that light can cross in less time than the time between them, then all observers agree on which event happened first. Cause always precedes effect. But if you could travel faster than light, you could create scenarios where effect precedes cause, where you arrive before you leave, where future events influence past events in ways that create logical paradoxes. Consider a simple example. You are on Earth. You send a signal to a spaceship moving away from Earth at a significant fraction of light speed. If that signal travels faster than light, there exist reference frames in which the signal arrives at the spaceship before it was sent from Earth. From the spaceship's perspective, the signal travels backward in time. Now imagine the spaceship immediately sends a faster-than-light reply back to Earth. From Earth's perspective, the reply might arrive before the original signal was sent. You receive a response to a message you have not yet transmitted. Cause and effect become tangled. The logical structure of time breaks down. This is not a flaw in special relativity. This is special relativity revealing something fundamental about the nature of time itself. Time is not a river that flows uniformly for all observers. It is a dimension of space-time, and its ordering is protected by the speed of light. The speed of light is not just a maximum velocity. It is the speed at which causality propagates. It is the speed at which information, influence, and the logical sequence of events can move through the universe. When you exceed it, you do not simply go faster, you violate the structure of reality. And yet, light itself does not experience this journey. A photon does not age. It does not perceive distance. It connects 2 points in space-time instantly from its own frame of reference, if such a frame can be said to exist. The photon simply is, existing simultaneously at all points along its world line, a timeless entity that bridges vast distances in what we perceive as years, but what it experiences as nothing. Light is the universe's way of connecting distant events while preserving causality. It moves fast enough to allow communication and interaction across space, but slow enough that cause always precedes effect, that the past remains distinct from the future, that the logical sequence of time remains coherent. When you look at a star, you're seeing light that left that star years ago. You're looking into the past. The star you see may no longer exist in its current form. It may have evolved, dimmed, or even exploded. But you will not know until the light from those events reaches you, travelling at exactly the speed required to preserve the causal order of the universe. You see the star as it was, not as it is, and this delay is not a limitation of telescopes or instruments. It is a fundamental feature of space-time. information cannot travel faster than light because the universe would become incoherent if it did. This is what light speed means. It is not about photons or electromagnetic waves specifically. It is about the maximum rate at which the universe permits cause to influence effect, at which information can propagate, at which one part of spacetime can interact with another. It is a property of geometry, of the way space and time are woven together into a unified whole. And it is absolute. It does not depend on technology or cleverness or willpower. It is built into the fabric of existence. The light from the most distant galaxies we can observe has been travelling for more than 13 billion years. Those photons were emitted when the universe was young, when the first stars were forming, when space was filled with hot, dense plasma that had only just become transparent to light. They travelled across an expanding universe, across distances that grew larger as they moved, finally arriving at our telescopes after a journey that spanned most of cosmic history. From our perspective, that journey took 13 billion years. From the photon's perspective, it happened instantly. Emission and absorption occurred at the same moment. The entire history of the universe, from its perspective, was compressed into a single eternal now. This is the journey that light makes. This is what it means to move at the speed of causality. And when scientists propose methods to travel faster than this, they are not proposing to make a longer journey shorter. They are proposing to change what a journey means. They are proposing to warp space-time so severely that the normal rules about distance and duration no longer apply in the straightforward way they do in flat, empty space. They are not trying to go faster than light. They are trying to restructure space itself so that light's speed becomes irrelevant. But the light remains, the speed remains, the barrier remains. And every photon that reaches your eye from the sun, from the stars, from the distant galaxies, testifies to the fact that the universe has a speed limit, and that limit is not arbitrary. It is the speed at which reality itself propagates. There is a wall built into the structure of reality, and it is made of energy. Not energy in the way you usually think of it, not the energy stored in gasoline or batteries or the kinetic energy of a moving car, but energy in a more fundamental sense. Energy is a relationship between mass, velocity, and the fabric of space-time itself. This wall cannot be seen or touched. It cannot be measured directly, but it can be felt in every particle accelerator on Earth, in every attempt to push matter closer to the speed of light, in the stubborn resistance the universe offers to anything trying to reach that final threshold. When you accelerate an object, you add energy to it. Push a shopping cart and it rolls forward. The energy from your muscles transfers into the cart's motion, and the cart moves faster. Push harder, and it moves faster still. The relationship seems straightforward. More force equals more speed. More energy equals higher velocity. At everyday speeds, this relationship holds almost exactly. Double the energy and you roughly double the speed. Triple the energy and the speed triples. The math is simple, the physics is intuitive, but this intuition is a lie, or at least an approximation that only works when speeds are small compared to the speed of light. As an object's velocity increases, something changes. The energy you add does not translate into speed as efficiently as it did before. Some of the energy goes into speed, but increasingly, more of it goes into something else. It goes into mass. Not mass in the sense that the object gains physical matter or becomes heavier on a scale, but mass in the sense that the object's resistance to further acceleration increases. Its inertia grows. From the perspective of an outside observer, the object behaves as though it is becoming more massive, requiring ever greater amounts of energy to achieve smaller and smaller increases in velocity. This effect is negligible at low speeds. A car travelling at 60 miles per hour has effectively the same mass as a car sitting still. The difference exists, but it is so tiny that no instrument could measure it. Even at the speeds achieved by fighter jets or rockets, the mass increase is insignificant. But as you approach a substantial fraction of the speed of a light, the effect becomes impossible to ignore. At 10% of light speed, an object's mass increases by about 0.5%. Still small, but measurable. At 50% of light speed, the mass increases by about 15%. At 90%, the mass has more than doubled. At 99%, the mass is 7 times greater than it was at rest. This is not a gradual climb. It is a curve that grows steeper and steeper, approaching vertical as velocity approaches light speed. At 99.9% of light speed, the mass factor is 22. At 99.99% it is 70. At 99.999%, it is 224. The closer you get to light speed, the more energy you must add to achieve even the tiniest increase in velocity. And at exactly light speed, the mass becomes infinite. The energy required to reach that speed becomes infinite. You cannot supply infinite energy. The wall is absolute. Particle physicists encounter this wall every day. Particle accelerators like the Large Hadron Collider routinely accelerate protons to speeds exceeding 99.9999% of the speed of light. At these velocities, the protons are moving so close to light speed that the difference is measured in fractions of a meter per second out of a total velocity of nearly 300,000 kilometers per second. The protons have so much kinetic energy that their effective mass is thousands of times greater than their rest mass. They carry energy equivalent to the kinetic energy of a flying mosquito, concentrated into particles so small that trillions of them would fit on the head of a pin. To accelerate these protons to such extreme speeds requires enormous machinery. The Large Hadron Collider is a ring 27 kilometers in circumference, lined with superconducting magnets cooled to temperatures colder than outer space. The protons are accelerated gradually over millions of circuits around the ring, gaining a tiny amount of energy with each pass. The entire facility consumes as much electricity as a small city. And even with all this energy, even with all this infrastructure, the protons never reach light speed. They approach it asymptotically, getting closer and closer but never arriving. Adding more energy makes them approach light speed more closely, but it does not make them reach it. The wall remains. This is not an engineering problem. It is not a limitation of current technology that might be overcome with better magnets or more efficient power sources. It is a fundamental feature of how mass and energy relate to velocity in a universe governed by special relativity. The equation that describes this relationship is one of the most famous in physics. E equals mc squared. Energy equals mass times the speed of light squared. But this equation, as it is usually written, describes only the rest energy of an object, the energy contained in its mass when it is not moving. The full equation, the one that includes motion, is more complex. It accounts for both the object's rest mass and its kinetic energy, and it reveals that as velocity approaches light speed, the total energy approaches infinity. You cannot reach infinity. You cannot even approach it in any practical sense. The energy required to accelerate a single proton to light speed exceeds the total energy output of every power plant on Earth. The energy required to accelerate a spacecraft with a human crew to light speed exceeds the total energy contained in all the matter in the solar system. These are not exaggerations. These are the actual consequences of the equations. The speed of light is not protected by some external barrier that clever engineering might bypass. It is protected by the structure of mass and energy themselves. Every joule of energy you add to an object moving near light speed goes almost entirely into increasing the object's effective mass, not its velocity. You're trying to accelerate something that is becoming infinitely heavy, and yet photons move at light speed effortlessly. They do not require infinite energy. They do not become infinitely massive. They simply move at light speed because that is the only speed at which they can exist. The difference is mass. Photons have no rest mass. They have energy and momentum, but no mass. An object with zero mass must move at light speed. An object with any mass at all, no matter how small, cannot reach light speed. There is no middle ground. The universe divides cleanly into two categories: massless particles that move at light speed and massive particles that cannot. This division has profound implications. It means that everything you have ever seen, touched or interacted with is fundamentally limited to speeds below light. Every atom in your body, every electron orbiting every nucleus, every molecule of air, every planet and star and grain of dust, all of it is confined to the subliminal realm, forever separated from the light speed realm by an unbridgeable gap. Matter can approach light speed but never reach it. Information can travel at light speed through massless particles, but structure, complexity, life, consciousness, all of these require matter, and matter is slow. This is the wall. It is not made of anything physical. It is made of geometry. It is made of the way space-time curves around mass and energy, the way time dilates and length contracts, the way the universe enforces a maximum speed for causality. You can throw as much energy as you want at a particle. and it will never cross that threshold. You will only make it heavier, more resistant to further acceleration, until the energy cost of each additional increment of speed becomes absurd, then ridiculous, then impossible. Consider what this means for interstellar travel. The nearest star system is 4 light-years away. To reach it in a reasonable human time frame, say 10 years, you would need to travel at 40% of light speed. At that velocity, the mass increase factor is about 1.1, meaning your spacecraft would effectively weigh 10% more than it does at rest. The energy required to accelerate it to that speed is colossal but not infinite. It could be calculated. It could, in principle, be achieved with advanced enough propulsion technology. But now consider the return journey. You must decelerate at your destination, which requires the same amount of energy you used to accelerate. Then you must accelerate again to return home, then decelerate again. Every phase of the journey requires enormous energy expenditure, and all of that energy must be carried with you or generated along the way. Now consider travelling at 90% of light speed to cut the journey time in half. The mass increase factor jumps to over 2. The energy required more than quadruples, and for what? You save 5 years on a 10-year journey. The energy cost increases exponentially while the time savings increase linearly. At 99% of light speed you could make the journey in just over 4 years, but the energy required would be more than 40 times greater than at 40% light speed. At 99.9%, the energy cost would be hundreds of times greater. You are running into the wall, and every step closer to it demands more energy than all the previous steps combined. This is why no serious proposal for interstellar travel involves speeds anywhere close to light speed. The most optimistic concepts aim for 10 to 20% of light speed, velocities that are still absurdly difficult to achieve, but at least theoretically within the realm of physics we understand. Even these modest goals require propulsion systems that do not yet exist, energy sources far beyond anything currently available, and engineering solutions to problems that have not been solved. And all of this effort, all of this energy, all of this technology would still leave the travellers moving at a fraction of light speed, taking decades to reach even the nearest stars. The wall is real. It is made of infinite energy, and it does not move. Every experiment, every observation, every particle collision confirms that the speed of light cannot be reached by anything with mass. The universe enforces this limit not through friction or resistance, but through the fundamental relationship between energy and mass. You cannot go faster because there is no faster. There is only heavier. The energy you add does not make you faster. It makes you more massive. And the more massive you become, the more energy you need to go even marginally faster. The process feeds on itself, creating a barrier that grows stronger the more you push against it. This is what scientists are trying to circumvent when they propose faster-than-light travel. They are not trying to break through the wall. They know the wall cannot be broken. They are trying to find a way around it, a geometric loophole that allows motion without acceleration, distance without velocity, travel without ever approaching the speed that cannot be reached. The universe is not a container. This is one of the most difficult concepts to grasp about the nature of reality, and it's essential to understanding how faster-than-light travel might theoretically be possible. When you imagine space, you probably picture an empty void, a vast three-dimensional volume in which objects exist and move. You imagine the stars scattered through this volume like islands in an ocean, separated by stretches of nothing. This picture is useful for everyday thinking, but it is fundamentally wrong. Space is not a backdrop against which events occur. Space is a participant. It is dynamic. It can bend, stretch, compress, and curve. And crucially, it can move. This insight came from Einstein's general theory of relativity, published in 1915, where special relativity describes how time and space behave for objects moving at constant velocities. General relativity describes how time and space respond to mass and energy. The central idea is that mass warps the geometry of space-time around it. A massive object like the Sun creates a curvature in space-time, a depression in the fabric of reality that extends outward in all directions. Objects moving near the Sun follow paths determined by this curvature. They are not being pulled by a force in the traditional sense. They are following the straightest possible path through curved space-time. We call this phenomenon gravity. When Earth orbits the Sun, it is not being held in place by an invisible rope or pulled by a mysterious attractive force. It is moving in a straight line through spacetime that happens to curve back on itself because the sun's mass has warped the geometry of the region. The curvature is real. It can be measured. Light passing near the sun bends because spacetime itself is bent. Time runs slower in stronger gravitational fields because the curvature of spacetime affects not just space but time as well. Clocks at sea level run slightly slower than clocks on mountaintops because they are deeper in Earth's gravitational well, deeper in the curved region of spacetime that Earth creates. This curvature is not something imposed on space from outside. It is an intrinsic property of spacetime itself. When physicists say that mass curves spacetime, they do not mean that spacetime is embedded in some higher dimensional structure that allows it to curve. They mean that the internal geometry of spacetime changes. Distances between points become different than they would be in flat space. Parallel lines can converge or diverge. The angles in a triangle no longer add up to exactly 180 degrees. These are geometric facts, measurable properties of the space itself, and if mass can curve spacetime, then in principle, other configurations of energy and matter might curve it in other ways. General relativity is a set of equations that relate the curvature of spacetime to the distribution of mass and energy within it. Given any configuration of mass and energy, you can calculate how spacetime curves in response. But you can also work backward. You can propose a particular curvature, a particular geometry of spacetime, and then solve the equations to find out what distribution of mass and energy would create that geometry. This is how physicists explore exotic solutions to Einstein's equations. They imagine geometries that have interesting properties, and then they ask what it would take to make those geometries real. Some solutions require ordinary matter and energy. A spherical mass creates the curved spacetime around a star. A rotating mass creates additional effects, twisting spacetime in ways that depend on the mass's angular momentum. These solutions describe the universe we observe. But other solutions require something stranger. They require negative energy densities, exotic matter with properties unlike anything that has ever been measured, configurations that may be mathematically possible but physically forbidden. And among these exotic solutions are geometries that allow for effective faster-than-light travel. The key insight is that there is no speed limit on spacetime itself. The speed of light is a limit on motion through space, but it is not a limit on how fast space can expand or contract. Consider the expansion of the universe. The space between distant galaxies is growing. The galaxies are not moving through space in the conventional sense. The space between them is increasing, and as it increases, the galaxies recede from one another. For galaxies that are sufficiently far away, the rate of recession exceeds the speed of light. A galaxy 10 billion light-years away is receding from us at more than twice the speed of light, because the space between us is expanding. This does not violate special relativity because the galaxy is not moving through space faster than light. Space itself is expanding, carrying the galaxy along with it. If space can expand, it can also contract. And if it can expand or contract uniformly, it can also expand and contract in specific regions while remaining flat elsewhere. This opens a conceptual possibility. Imagine a region of space in front of a spacecraft that is contracting, bringing distant points closer together. Simultaneously, imagine a region of space behind the spacecraft that is expanding, pushing points farther apart. The spacecraft itself remains stationary relative to the space immediately around it, sitting in a flat, unwarped region between the contracting space ahead and the expanding space behind. The spacecraft does not move through space. Space moves around the spacecraft. The distance to the destination shrinks in front while the distance from the origin grows behind. The net effect is that the spacecraft covers vast distances without ever accelerating, without ever moving through space at speeds approaching light. This is the principle behind the Alcubierre warp drive proposed by physicist Miguel Alcubierre in 1994. Alcubierre constructed an exact solution to Einstein's field equations that describes this geometry. The solution is mathematically valid. It satisfies all the requirements of general relativity. A spacecraft in an Alcubierre bubble would experience no acceleration, no time dilation, and no increase in mass. From the perspective of passengers inside the bubble, they would be at rest, sitting in a region of flat space-time. But from the perspective of an outside observer, the bubble would be moving, covering distance at rates that could theoretically exceed the speed of light by arbitrary factors. 10 times light speed, 100 times, 1,000 times. The mathematics permits any velocity, but the mathematics also reveals the cost. To create the Alcubierre geometry, to warp space in the required way, you need to thread the region around the spacecraft with exotic matter that has negative energy density. Not merely a little negative energy, but enormous quantities of it, distributed in a specific configuration that maintains the warp bubble while allowing the spacecraft to remain in a flat region at the center. Negative energy density means that the matter exerts negative pressure, that it gravitationally repels rather than attracts, that it violates energy conditions that have held true in every physical system ever observed. Negative energy densities are not strictly forbidden by quantum mechanics. The Casimir effect, a phenomenon where two uncharged metal plates placed very close together in a vacuum experience an attractive force, can be interpreted as arising from negative energy density in the space between the plates. But the amount of negative energy involved is infinitesimal, and it exists only in highly constrained configurations over microscopic distances. Scaling this up to the macroscopic level, creating enough negative energy to warp space-time around a spacecraft, would require technology so far beyond current physics that it borders on magic. You would need to manipulate quantum fields in ways that have never been demonstrated, stabilize configurations that want to collapse, and somehow contain energy densities that would be catastrophically unstable. Even if you could create the exotic matter, you would need to arrange it precisely to generate the correct space-time geometry. The warp bubble must contract space ahead and expand space behind, but it must do so smoothly, without creating regions of infinite curvature or singularities that would destroy the spacecraft. The energy distribution must be stable over the duration of the journey, maintaining its configuration despite the dynamic geometry of space-time around it, and you must be able to turn it on and off to enter and exit the warp bubble without violating causality or creating closed time-like curves that allow travel into the past. These are not minor technical hurdles. They are not problems that better engineering or more powerful technology can solve. They are problems that arise from the fundamental structure of physics as we currently understand it. Exotic matter may not exist. Negative energy densities in the required quantities may be forbidden by principles we have not yet discovered. The energy conditions violated by the Alcubierre solution may be absolute, not merely practical limits, but fundamental constraints that prevent certain geometries from ever being realized. And yet, the solution exists, the mathematics is valid, general relativity permits it. This is what scientists mean when they say they have found a method to travel faster than light. They have found a configuration of space-time that, if it could be created, would allow effective faster-than-light travel without violating the local speed limit. The spacecraft never moves faster than light through the space around it. Space itself does the moving. The distinction is subtle but crucial. You're not breaking the rule. You're using a different rule, one that applies to space-time itself rather than to objects moving through it. But using that rule requires resources that do not exist and may never exist. It requires bending space so severely that the fabric of reality itself becomes exotic, unstable, and possibly impossible. The loophole is real, but the door it opens leads to a place we cannot go. The geometry of a warp bubble is not simple. It is not a matter of pushing space forward and pulling space backward in some uniform, symmetrical way. The curvature must be carefully shaped, with specific gradients and transitions that maintain a region of flat space-time at the center, while creating the expansion and contraction needed to produce net motion. The equations that describe this geometry are precise. They specify exactly how space-time must curve at every point around the spacecraft, how the curvature must change with distance from the center, and how the entire structure must move through the surrounding flat space-time without disrupting itself. Imagine a wave moving through water. The water itself does not travel with the wave. Individual water molecules move up and down, oscillating in place, while the wave pattern propagates forward. The wave is a disturbance in the medium, a travelling configuration of motion that moves through the water without carrying the water along with it. A warp bubble is similar, except the medium is space-time itself. The bubble is a travelling distortion in the geometry of space-time, a region where space contracts ahead and expands behind, creating a wave of curvature that propagates through the universe. The spacecraft sits at the crest of this wave, in the flat region between the contraction and expansion, riding the distortion without ever moving relative to the space immediately around it. The shape of this distortion is critical. If the contraction ahead is too steep, if space compresses too rapidly over too short a distance, the curvature becomes infinite and a singularity forms. If the expansion behind is too gradual, it does not produce enough net motion to propel the bubble forward at the desired speed. The geometry must be balanced precisely, with smooth transitions that avoid infinite curvature while still generating the necessary distortion. Alcubierre's original solution achieved this balance, but it required exotic matter distributed in a thin shell around the spacecraft, with energy densities that increased without bound as the shell was made thinner. The amount of exotic matter required in Alcubierre's original formulation was staggering. Early calculations suggested that warping space around a spacecraft 100 meters in diameter would require negative energy equivalent to the total mass energy of Jupiter, if not more, and this energy would need to be maintained continuously throughout the journey. The spacecraft would need to generate or carry this enormous quantity of exotic matter, arrange it in the precise configuration required to maintain the warp geometry, and keep it stable while travelling at speeds exceeding light. The engineering challenges were overwhelming. The energy requirements were beyond anything remotely achievable. The solution was mathematically valid but practically absurd. This is where recent work has focused. Physicists have refined the Alcubierre geometry, finding variations that require less exotic matter or distribute it differently. In 2021, researchers showed that by changing the shape of the warp bubble, making it thicker in some dimensions and thinner in others, the energy requirements could be reduced significantly. Instead of needing the mass energy of Jupiter, the modified design might require only the mass energy of a large asteroid, or even less depending on further optimizations. This is still an enormous amount of energy, but it is several orders of magnitude smaller than the original estimate. The improvement is real, the reduction is substantial, and yet the fundamental problem remains. The problem is not the quantity of exotic matter. The problem is that exotic matter probably does not exist in the forms and quantities required. Negative energy density is not merely rare or difficult to produce, it is something that may be fundamentally forbidden by the structure of quantum field theory. The Casimir effect, often cited as evidence that negative energy is possible, involves only tiny amounts of negative energy localized between conducting plates at microscopic separations. Scaling this up to macroscopic distances and energy densities is not a matter of building bigger plates or more powerful equipment. It is a matter of asking whether the laws of physics permit such configurations to exist at all. Quantum field theory places limits on how much negative energy can exist in a given region, and for how long. These limits are called quantum energy inequalities, and they arise from the fundamental properties of quantum fields. Negative energy can exist temporarily over small distances, but the more negative energy you want, and the longer you want it to last, the more restricted the possibilities become. The inequalities suggest that concentrating large amounts of negative energy in a macroscopic region for an extended period is impossible. Not merely impractical, but prohibited by the same principles that govern particle creation and vacuum fluctuations. Even if exotic matter could be created, stabilizing it would present additional challenges. Negative energy densities are inherently unstable. They want to collapse, to dissipate, to equalize with the surrounding vacuum. Maintaining a warp bubble would require constant input of energy to counteract this instability, to keep the exotic matter from decaying or spreading out into configurations that no longer produce the required geometry. You would need active control systems that adjust the energy distribution in real time, responding to fluctuations and perturbations that could destabilize the bubble, and these control systems would themselves need to operate faster than the speed at which instabilities propagate, which might require faster than light communication, creating a circular dependency where you need faster than light capability to maintain the faster than light drive. There is also the question of how you enter and exit the warp bubble. If you are sitting in flat space-time and you want to create a warp bubble around yourself, you must somehow thread your local region with exotic matter, generating the negative energy densities needed to warp space. But how do you generate negative energy from a position of rest? How do you create the initial distortion when you do not yet have the exotic matter configuration needed to sustain it? Alcubierre's solution describes the geometry of a warp bubble that is already formed and travelling, but it does not describe how such a bubble could be created from normal space-time. It is a solution that describes motion but not initialization. Similarly, Once you're inside the warp bubble and travelling at 10 times the speed of light, how do you stop? To exit the bubble, you must dissipate the exotic matter, allowing space-time to return to its flat configuration. But the exotic matter is what maintains the bubble's structure. Remove it too quickly and the bubble collapses catastrophically, potentially releasing enormous amounts of energy in an uncontrolled manner. Remove it too slowly, and you coast at faster than light speeds with no way to decelerate or navigate. The process of entering and exiting the warp state may be as difficult, or more difficult, than maintaining the warp itself. And then there is the question of navigation. A spacecraft inside a warp bubble is causally disconnected from the space ahead of it. The region of contracted space in front acts as a horizon, a boundary beyond which information cannot reach the spacecraft. Light emitted from objects ahead cannot penetrate the contracting space to reach the flat region where the spacecraft sits. You are travelling blind, unable to see where you're going or detect obstacles in your path. You cannot steer, you cannot change course, you cannot even know if you're still on the correct trajectory. Once the warp bubble is formed and set in motion, you're committed to that trajectory with no way to adjust it based on external information. This creates severe practical limitations. Interstellar space is not empty. It contains dust, gas, stray atoms, micrometeoroids, and larger debris. Travelling at 10 times the speed of light through such a medium would be catastrophic if you encountered any significant mass. A single grain of sand encountered at 10 times light speed would release energy equivalent to a nuclear explosion, and because you cannot see ahead, you cannot avoid these collisions. You can only hope that your trajectory was calculated correctly, and that the space you are traversing is sufficiently empty that you do not encounter anything substantial. The warp bubble itself might also interact with the surrounding spacetime in unexpected ways. As it moves, it drags spacetime along with it, creating distortions that propagate outward. These distortions carry energy. When the bubble finally stops and dissipates, that energy must go somewhere. Some calculations suggest that the energy accumulated at the front of the bubble during faster-than-light travel would be released as a burst of high-energy particles and radiation when the bubble collapses. This burst could be intense enough to sterilize planets, destroy space stations, or obliterate anything in the direction of travel. The warp drive might function as a weapon whether you intend it to or not. These are not minor details. They are fundamental challenges that arise directly from the physics of warped space-time. Every refinement to the Alcubierre geometry, every reduction in the exotic matter requirements, every optimization of the bubble shape must contend with these issues. The mathematics allows for solutions, but the solutions come with costs that may be unpayable and consequences that may be unacceptable. The warp drive is not a straightforward technology waiting to be developed. It is a theoretical construct that exploits a loophole in general relativity while creating a cascade of problems that have no obvious resolutions. And yet, the fact that the solution exists at all is remarkable. It means that the universe, as described by general relativity, does not absolutely forbid faster-than-light travel. It means that the speed of light is a local limit, a constraint on motion through space, but not a limit on the geometry of space itself. It means that the structure of space-time is more flexible than intuition suggests, more capable of exotic configurations than everyday experience would imply. The warp drive may be impossible to build, but it is not impossible to describe, and that distinction, narrow as it may be, is the difference between absolute prohibition and theoretical possibility. Energy is not free. This is perhaps the most fundamental constraint in all of physics, more absolute than any speed limit, more unyielding than any material strength. Every action requires energy. Every change in velocity, every change in configuration, every departure from equilibrium demands that energy be supplied from somewhere. The universe keeps meticulous accounts. Energy can be transformed from one form to another, transferred from one system to another, but it cannot be created or destroyed. When you propose to warp space-time, to compress space ahead, and expand space behind, you are proposing to change the geometry of reality itself. And that change requires energy on a scale that defies comprehension. To understand the energy requirements of a warp drive, you must first understand what energy means in the context of space-time curvature. In general relativity, mass and energy are equivalent. They are different manifestations of the same underlying quantity. When mass curves space-time, it does so because mass is concentrated energy, and energy is the source of gravitational fields. A kilogram of matter contains an amount of energy given by Einstein's equation, E equals mc squared, where c is the speed of light. For 1 kilogram, this equals approximately 9 times 10 to the 16th joules, or 90 petajoules. This is roughly the energy released by a 20 megaton nuclear weapon. Every kilogram of matter you see around you contains this much energy locked in its mass. Now consider what it means to warp space-time around a spacecraft. You're not simply moving mass from one place to another. You're changing the geometry of space itself, curving it in ways that do not correspond to any natural distribution of ordinary matter. In Alcubierre's original formulation, this requires threading the region around the spacecraft with exotic matter, matter with negative energy density. The negative energy is what produces the unusual curvature, the contraction ahead and expansion behind that generates the warp effect. And the amount of negative energy required is directly related to how severely you need to warp space and how large a region you need to warp. The initial calculations for an Alcubierre drive were staggering. To create a warp bubble around a spacecraft 100 meters in diameter, traveling at 10 times the speed of light, the original geometry required negative energy equivalent to the total mass energy of Jupiter. Jupiter's mass is approximately 2 times 10 to the 27th kilograms. Multiply this by c squared, and you obtain an energy of roughly 2 times 10 to the 44th joules. To put this in perspective, the Sun outputs approximately 4 times 10 to the 26 joules per second. It would take the Sun more than 1 billion years to output the energy equivalent to Jupiter's mass. And this is the energy you would need just to create the warp bubble, not to maintain it, not to accelerate to the desired velocity, but simply to establish the initial geometric distortion. This is not an engineering problem. It is not a question of finding more efficient power sources or better energy storage systems. It is a question of whether the energy exists in any accessible form. The total mass energy of Earth is approximately 5 times 10 to the 41 joules. The total mass energy of the Sun is approximately 2 times 10 to the 47 joules. You would need to convert a substantial fraction of a star's mass entirely into negative energy, and somehow arrange it in the precise configuration required to maintain a warp bubble. There is no known process that could accomplish this. There is no mechanism by which ordinary matter could be converted into the exotic matter required. The energy cost is not merely large, it is cosmological. Recent refinements have reduced these requirements significantly. By reshaping the warp bubble, making it less symmetrical and more elongated, physicists have found geometries that require far less exotic matter. Some optimized designs suggest that the energy requirement could be reduced to the mass energy equivalent of a large spacecraft, perhaps several hundred kilograms. This is still enormous by human standards, equivalent to thousands of nuclear weapons, but it is many orders of magnitude less than the mass of Jupiter. The improvement is real. The reduction changes the conversation from impossible to merely absurd. But even these reduced requirements come with caveats. The optimized geometries often produce warp bubbles that are thinner, more fragile, more sensitive to perturbations. They may be more difficult to stabilize, more prone to collapse, more vulnerable to interactions with the surrounding spacetime, and they still require exotic matter, which remains the fundamental obstacle. Reducing the quantity of exotic matter needed does not solve the problem of how to create exotic matter in the first place. It is like reducing the amount of unobtainium required to build a spacecraft. The reduction is mathematically interesting, but it does not make unobtainium real. There is also the question of where the energy comes from during the journey. A warp bubble does not coast. It is not a configuration that, once established, persists without further input. The exotic matter must be maintained. The geometry must be stabilized against fluctuations. Any interaction with the surrounding spacetime, any gravitational influence from nearby masses, any quantum fluctuation in the vacuum, all of these can perturb the bubble and must be corrected. This requires continuous energy input, a power supply that operates throughout the journey and adjusts the exotic matter distribution in real time. The spacecraft must carry this power supply or extract energy from the vacuum or from the spacetime geometry itself. None of these options are straightforward. If the spacecraft carries its energy supply, that energy has mass, and that mass contributes to the total energy requirement. The more energy you carry, the more mass you have, and the more energy you need to warp space around that mass. The relationship is non-linear. Adding energy to enable longer journeys increases the difficulty of initiating the warp in the first place. You could find yourself in a situation where the energy needed to carry the energy exceeds the energy you are carrying, a recursive problem with no solution. If the spacecraft extracts energy from the vacuum, it must do so without violating the energy conditions that prohibit large-scale negative energy densities. The Casimir effect shows that small amounts of energy can be extracted from the quantum vacuum under specific conditions, but scaling this up to the macroscopic level is not proven possible. You might be able to extract enough energy to power a small device, but extracting enough to maintain a warp bubble around a spacecraft is many orders of magnitude beyond what quantum field theory suggests is possible. The vacuum is not an infinite reservoir of free energy. It has structure, limits, and conservation laws that constrain what can be extracted and how. If the spacecraft extracts energy from the spacetime geometry itself, it is essentially harvesting the gravitational potential energy of the curved region. But this energy came from somewhere. It was supplied when the warp bubble was created. Extracting it during the journey might weaken the bubble, reduce its effectiveness, or cause it to decay prematurely. You cannot get more energy out of a system than you put into it. The geometry might store energy temporarily, but it cannot generate energy from nothing. Even if all these problems were solved, even if exotic matter existed and could be produced in the required quantities, even if the energy could be supplied and maintained throughout the journey, there is still the question of dissipation. Warping spacetime is a form of work performed against the natural tendency of spacetime to remain flat. When you release the warp, when the bubble collapses and spacetime returns to its unwarped state, the energy stored in the geometric distortion must go somewhere. It might be radiated as gravitational waves, as electromagnetic radiation, as high-energy particles. The sudden release of energy equivalent to hundreds of kilograms of matter, or more, would not be subtle. It would be violent. It would be detectable across vast distances. It might be dangerous to anything nearby. Some models suggest that the energy accumulated at the leading edge of the warp bubble during faster-than-light travel would be concentrated and blue-shifted, transformed into a beam of high-energy radiation that could incinerate planets. Others suggest that the bubble's collapse would generate gravitational shock waves that propagate outward, distorting spacetime in unpredictable ways. These are not speculative concerns. They are direct consequences of the energy conservation laws applied to the warp geometry. The energy must be accounted for. It cannot simply vanish when the journey ends. This is the energy cost. It is not a single payment made at the beginning of the journey. It is a continuous demand that persists from initiation through travel to termination. It is a requirement that exceeds anything humans have ever generated, harnessed, or controlled. It is a cost measured in planetary masses, in stellar outputs, in energy densities that may be physically impossible to achieve. And even if future civilizations develop technologies that make such energy accessible, even if exotic matter turns out to be real and controllable, the energy cost ensures that faster-than-light travel would never be casual, never be routine, never be easy. It would remain an extraordinary act, a departure from ordinary physics that demands extraordinary resources. The universe does not prohibit faster-than-light travel outright, but it prices it beyond reach. The loophole exists, but the toll is unpayable. And so the stars remain distant, the galaxies remain isolated, and the speed of light remains the effective boundary of all practical travel, not because the laws forbid circumventing it, but because the cost of circumvention exceeds everything we have or are likely ever to have. There is a difference between rare and impossible, between difficult and forbidden. Exotic matter occupies the uncertain space between these categories, a concept that is mathematically permissible, theoretically plausible, but observationally absent. It is matter with properties that violate the energy conditions that ordinary matter obeys, matter that gravitationally repels rather than attracts, matter with negative energy density that creates effects opposite to everything you have ever experienced, and without it, the warp drive remains a solution to equations that describes nothing real. Energy density is a simple concept at its core. It measures how much energy exists in a given volume of space. Ordinary matter has positive energy density. A kilogram of iron, a litre of water, A cubic meter of air, all of these contain energy distributed through their volume. The energy might be the rest mass energy of the particles, the kinetic energy of their motion, the potential energy of their interactions. But it is always positive. There is energy there. The presence of matter means the presence of energy, and energy density is never negative. Negative energy density means that a region of space contains less energy than empty space would contain. This sounds paradoxical. How can something contain less than nothing? The resolution lies in quantum field theory, where the vacuum is not truly empty. The vacuum is filled with quantum fields in their lowest energy state, fields that constantly fluctuate, creating virtual particle pairs that appear and disappear on timescales too brief to violate conservation laws. These fluctuations contribute to the energy of the vacuum. They give empty space a baseline energy density that is small but non-zero. And if you can reduce the energy in a region below this baseline, if you can suppress the vacuum fluctuations in a localized volume, you create a region with negative energy density relative to the surrounding vacuum. The Casimir effect demonstrates this principle. Two parallel conducting plates placed very close together in a vacuum experience an attractive force that cannot be explained by any classical mechanism. The force arises because the metal plates restrict which wavelengths of virtual particles can exist between them. Only fluctuations with wavelengths that fit precisely between the plates are permitted. Outside the plates, all wavelengths are possible. This means the vacuum between the plates has lower energy density than the vacuum outside, creating a pressure difference that pushes the plates together. The effect has been measured. It is real, and it proves that negative energy density, at least in a limited sense, is physically achievable. But the Casimir effect involves infinitesimal amounts of negative energy distributed over microscopic distances. The force between the plates is detectable only when they are separated by distances comparable to the wavelength of light, less than a micrometer. The energy deficit is correspondingly tiny, far too small to have any gravitational effect or to warp space-time in any measurable way. To create a warp bubble, you would need to scale this effect up by more than 30 orders of magnitude, creating negative energy densities strong enough to curve space-time macroscopically and sustaining them over volumes large enough to enclose a spacecraft. This is where the concept strains against the boundaries of known physics. Quantum field theory allows for temporary localized violations of positive energy density, but it also imposes constraints known as quantum energy inequalities. These inequalities place limits on how much negative energy can exist, how long it can persist, and how it can be distributed in space. The more negative energy you want, and the larger the volume over which you want it, the more restrictive the inequalities become. They suggest that concentrating the negative energy densities required for a warp drive over macroscopic volumes for the duration of an interstellar journey may be fundamentally impossible, not merely beyond current technology, but prohibited by the structure of quantum fields themselves. Even if quantum energy inequalities allow for some exotic matter configurations, creating and controlling such matter would require technologies that do not exist. You would need to manipulate quantum fields at energy scales far beyond what particle accelerators can achieve. You would need to maintain coherent quantum states over macroscopic distances and timescales, preventing decoherence and collapse. You would need to shape the negative energy distribution precisely, arranging it in the specific geometry required to produce the warp bubble. And you would need to stabilize this configuration against the natural tendency of quantum systems to evolve toward equilibrium, toward states with positive energy density and minimum free energy. There is no known mechanism for doing this. Proposals exist, speculative ideas involving squeezed quantum states, vacuum engineering, or manipulation of the zero-point energy of fields, but all of these remain theoretical. No experiment has produced negative energy in quantities exceeding the Casimir effect. No observation has detected exotic matter occurring naturally, and while absence of evidence is not evidence of absence, the complete lack of any observation of macroscopic negative energy over more than a century of precise measurements suggests that if exotic matter exists, it is either extremely rare or actively suppressed by physics we do not yet understand. Consider what exotic matter would mean for the universe if it were common. Negative energy density gravitationally repels. A concentration of exotic matter would push ordinary matter away rather than attracting it. Regions of space containing exotic matter would be voids, devoid of galaxies, stars, and planets. But we observe no such voids. We observe that gravity is universally attractive at macroscopic scales. Every mass attracts every other mass. Galaxies cluster, stars orbit, planets pull on moons. The universe behaves as though all matter has positive energy density, and negative energy, if it exists at all, is confined to quantum scales where its effects are negligible. This universal absence is telling. It suggests that exotic matter, in the quantities and configurations required for a warp drive, may be forbidden by principles deeper than those encoded in the equations we currently use. Energy conditions are not arbitrary rules imposed on general relativity. They emerge from reasonable physical assumptions about the behavior of matter and fields. The weak energy condition states that energy density should be non-negative in any reference frame. The null energy condition states that energy flowing along light-like paths should be non-negative. These conditions are violated by exotic matter, but they are satisfied by every form of ordinary matter and every field we have observed. Violating them may require more than clever engineering. It may require rewriting the foundations of physics. There is also the problem of stability. Even if exotic matter could be created, it would be energetically unfavourable. Systems evolve toward lower energy states. A region with negative energy density is a higher energy state relative to the vacuum. It would want to decay, to emit particles or radiation until the energy density rises back to positive values. Preventing this decay would require constant input of energy, or the imposition of some exotic constraint that prevents the natural evolution of the quantum fields. You would need to fight against the fundamental tendency of physical systems to reach equilibrium, and even if you stabilize the exotic matter, you would need to shape it. The warp bubble requires a specific distribution of negative energy, not a uniform sphere or a random configuration, but a carefully structured shell with density gradients that produce the correct space-time curvature. Creating this structure would be like sculpting with quantum fields, adjusting energy densities at every point in space to match the requirements of the geometry. The precision required would be extraordinary. A small error in the distribution could produce the wrong curvature, destabilizing the bubble or creating singularities that destroy the spacecraft. These are not engineering challenges. They are challenges that question whether the entire concept is physically realizable. Exotic matter may be allowed by the mathematics of general relativity and quantum field theory, but that does not mean it's allowed by nature. There may be principles we have not yet discovered, conservation laws we have not yet identified, that prohibit the creation of negative energy densities in the quantities and configurations required. The warp drive may remain forever a mathematical curiosity, a solution to equations that describes nothing that can exist. This is the problem with exotic matter. It is the foundation of every faster-than-light scheme based on warping space-time, and it is the weakest link in every proposal. Without exotic matter, the warp bubble cannot form. Without exotic matter, space cannot be compressed and expanded in the necessary ways. Without exotic matter, faster-than-light travel reverts to impossible, not because of speed limits, but because the mechanism itself cannot be built. And exotic matter, for all the theoretical possibilities, remains something we cannot create, cannot control, and may never be able to produce. The equations allow it. Reality does not provide it. And in the gap between what is mathematically permissible and what is physically real, the warp drive remains suspended, a method revealed in theory but absent in practice. Time is not what you think it is. You experience time as a river flowing in one direction, carrying you from past through present toward future. Events happen in sequence. Causes precede effects. You break an egg and then it splatters, never the reverse. You are born before you die. You read the beginning of a sentence before you reach its end. This ordering feels absolute, built into the fabric of existence itself. But it is not absolute. It is a consequence of the speed of light, a feature that emerges from the structure of space-time, and it is protected only as long as nothing travels faster than light. When you exceed that speed, even theoretically, the ordering of events becomes ambiguous, cause and effect become negotiable, and the logical structure of reality begins to unravel. Special relativity revealed that time is relative. Two observers moving at different velocities will disagree about the duration between events, about whether two distant events happen simultaneously, even about the order in which some events occurred. But these disagreements are constrained. For any two events where one could causally influence the other, where a signal travelling at light speed or slower could travel from the first event to the second, all observers agree on the ordering. The first event happens first. The second event happens second. The order is preserved across all reference frames. This is not coincidental. This is what it means for the universe to have a causal structure. The speed of light is not just a speed limit. It is the speed at which causality propagates. Now imagine you have a warp drive. You leave Earth and travel to Proxima Centauri 4 light-years away in 6 months. From Earth's perspective, you have travelled faster than light. A light signal sent when you departed will take 4 years to reach Proxima Centauri, but you arrive in 6 months. You have outpaced light. You have crossed a distance that should take 4 years in a fraction of that time, and this is where the problems begin. Consider an observer on a spacecraft moving at a significant fraction of light speed relative to Earth. From this observer's reference frame, events on Earth and events at Proxima Centauri have a different time ordering than they do from Earth's frame. What appears simultaneous to someone on Earth might appear sequential to the moving observer. What appears to happen in one order from Earth's perspective might appear to happen in a different order from the spacecraft's perspective. This is standard special relativity. It causes no paradoxes as long as no information travels faster than light, because the disagreements only affect events that cannot causally influence each other. But if you can send a faster than light signal, you can create a scenario where the signal arrives before it was sent. The moving observer sees your departure from Earth and your arrival at Proxima Centauri in a different temporal order than Earth does. If they send a faster than light signal back to Earth timed to their observation of your arrival, that signal, from Earth's perspective, might arrive before you originally left. The reply reaches Earth in the past. You receive a response before you sent the message. Causality is violated. This is not a minor technical issue. This is a fundamental breakdown in the logical structure of time. If effects can precede their causes, then the concept of causality loses meaning. You could receive information from the future, use that information to change your actions, and prevent the future event that sent the information. You could kill your grandfather before he meets your grandmother. You could destroy the warp drive before it was built. The universe would contain contradictions, events that both happened and did not happen, timelines that branch and merge in ways that make no coherent sense. Physics does not prohibit time travel in all forms. General relativity permits solutions where closed time-like curves exist, paths through space-time that loop back on themselves, allowing an observer to travel into their own past. These solutions are exotic. They require rotating black holes or wormholes or other extreme configurations of space-time, and they all raise the same causal paradoxes. If you can travel to your past, you can change events that led to your decision to travel, creating contradictions. The universe would need some mechanism to prevent these contradictions, some principle that enforces consistency, even when the geometry permits paradoxes. One proposed resolution is the Novikov self-consistency principle, which states that any action taken by a time traveler was always part of history. You cannot change the past because anything you do in the past was already done. If you travel back in time, you were always there in the past and your actions contributed to the timeline you remember. This preserves consistency, but eliminates free will in a disturbing way. You cannot choose to act differently, because your actions are predetermined by the requirement that they lead to the future you came from. The universe becomes a closed loop where causes and effects are circular, each producing the other. Another resolution is to reject closed time-like curves entirely, to impose additional constraints on space-time that prevent their formation. This is the chronology protection conjecture, proposed by Stephen Hawking, which suggests that the laws of physics contain mechanisms that prevent time travel even when the equations of general relativity permit it. Quantum effects might destabilize wormholes before they can be used for time travel. Exotic matter configurations might collapse before closed time-like curves form. The universe might have built-in safeguards that protect causality at all costs. But faster-than-light travel via a warp drive does not obviously create closed time-like curves in the same way that wormholes or rotating black holes do. The warp bubble moves through space-time without creating loops or connections between different times. From the perspective of someone inside the bubble, time flows normally, forward from past to future, just as it does in ordinary space-time. The bubble itself does not travel backward in time. It travels forward, covering space faster than light would, but always moving from earlier times to later times along its own world line. The problem arises when you combine faster-than-light travel with the relativity of simultaneity. Different observers disagree about what now means at distant locations. An event that is happening now at Proxima Centauri from Earth's perspective might have already happened or might not have happened yet from the perspective of a moving observer. If you can travel faster than light, you can exploit these disagreements to send messages into the past. You travel to Proxima Centauri faster than light, and then someone on Proxima Centauri travels back to Earth faster than light, using a trajectory calibrated to a different reference frame. The combination of two faster-than-light trips, neither of which individually violates causality, produces a closed loop in time. This means that faster-than-light travel and causality are in tension. You can have one or the other, but not both. If the universe permits faster-than-light travel, it must either accept causal paradoxes or impose additional constraints that prevent those paradoxes from occurring. Perhaps faster-than-light travel is only possible in certain reference frames. Perhaps it requires so much energy that it can only be used once, preventing the closed loops. Perhaps the exotic matter required to create a warp bubble also prevents the bubble from being used in ways that violate causality. These are speculative solutions to a problem that arises directly from the structure of spacetime. Some physicists argue that causality is so fundamental that any mechanism allowing faster-than-light travel must contain hidden constraints that prevent paradoxes. The universe might permit warp drives in principle, but only under conditions that make them useless for time travel. Others argue that causality violations are signs that the proposed mechanism is unphysical, that the universe simply does not allow the configurations required to produce them. The warp drive might be mathematically valid but physically forbidden, not because of energy requirements or exotic matter, but because permitting it would break causality. This is a deeper problem than the energy cost or the exotic matter. Those are practical obstacles, challenges that might be overcome with advanced technology or new discoveries. The causality problem is conceptual. It questions whether faster-than-light travel is consistent with the logical structure of time. It suggests that the universe may not permit certain configurations, not because they are difficult to achieve, but because they lead to contradictions that cannot be resolved. The equations allow the solution, but reality may not. And this brings you back to the original question. What does it mean when scientists say they have revealed a method to travel 10 times faster than light? It means they have found a mathematical solution that describes a geometry of space-time where such travel appears possible. But it does not mean the solution is physical. It does not mean the universe permits that geometry to be created. And it does not mean that even if it could be created, it would function in the way the equations suggest without breaking causality and plunging the universe into paradox. Strip away the mathematics, the exotic matter, the energy requirements, and the causal paradoxes, and you are left with a simpler question. What would it actually mean if humans could travel 10 times faster than light? Not what would it mean for physics, not what it would imply about space-time or quantum fields, but what would it mean for human life, for exploration, for the future of the species? This is the question that motivates all the research, all the speculation, all the headlines about faster-than-light travel, and the answer is more complicated than it appears. 10 times the speed of light sounds fast. It sounds like a dramatic improvement over the speeds humans can currently achieve. The Parker Solar Probe, the fastest human-made object, travels at less than 0.1% of light speed. 10 times light speed is more than 10,000 times faster. It is a number so large that it seems to change everything. But consider what it actually allows. The nearest star system, Proxima Centauri, is 4.2 light-years away. At 10 times light speed, you could reach it in 5 months. This is not instantaneous. It is not trivial. It is 5 months of travel through interstellar space, 5 months during which you cannot turn back easily, 5 months of confinement in a spacecraft surrounded by vacuum. 5 months is within the range of human endurance. Astronauts have spent longer periods on the International Space Station. Antarctic research teams have spent entire winters isolated at remote bases. Submarines have remained at sea for months without surfacing. 5 months is long, but it is not impossible. It is not a journey that requires generations or suspended animation, or accepting that everyone you know will age decades while you travel. It is a journey that a person could make and return from within their own lifetime, seeing the results, experiencing the destination, coming home to a world that has not moved on without them. But Proxima Centauri is the nearest star. The next nearest stars are farther. Sirius is 8.6 light-years away. At 10 times light speed, 10 months. Vega is 25 light-years away, 2.5 years. Betelgeuse is 550 light-years away, 55 years. The centre of the Milky Way galaxy is 26,000 light-years away, 55 years, 2,600 years. Andromeda, the nearest large galaxy, is 2.5 million light-years away, 250,000 years. Even at 10 times the speed of light, the universe remains vast. Most of it remains unreachable within a human lifetime. Most of it remains isolated beyond any practical journey. 10 times light speed makes the very nearest stars accessible. It turns a handful of stellar systems from theoretical destinations into places a human could actually visit. But it does not make the galaxy accessible. It does not turn interstellar travel into something routine or casual. It does not change the fundamental fact that space is mostly empty, that distances between stars are measured in years even when travelling faster than light, and that the vast majority of the universe remains far beyond reach. Now consider what it would actually take to make such a journey. Even if exotic matter existed, even if the energy requirements could be met, even if the warp drive functioned as the mathematics suggests, you would still need a spacecraft. You would need life support, navigation, communication systems, radiation shielding, supplies for months of travel. You would need to survive in an environment where there is no atmosphere, no gravity unless artificially generated, no sunlight except what you bring with you. The engineering challenges of sustaining human life in deep space do not disappear just because you can travel faster. They remain, perhaps even intensify, because any failure during a faster-than-light journey leaves you stranded light-years from help. And you would be travelling alone in a way that no human has ever been alone. On Earth, even in the most remote locations, you are part of a connected world. Radio signals reach you, satellites track your position, rescue is possible, even if difficult. In interstellar space, light takes years to cross the distances. A radio signal sent from Proxima Centauri takes 4 years to reach Earth. If something goes wrong during your journey, if the warp drive fails, if life support malfunctions, if the spacecraft is damaged, there is no rescue. There is no communication with home except messages that take years to arrive. You're isolated in a way that is absolute, separated from the rest of humanity by distances that make Earth's oceans look like puddles. This isolation changes the meaning of exploration. When humans explored Earth, they could return. Ships crossed oceans and came back. Expeditions reached poles and returned with their findings. Even the Apollo missions to the Moon, as distant and dangerous as they were, kept Earth visible in the window, a sphere of life hanging in the blackness, reachable in 3 days if something went wrong. But interstellar travel, even at 10 times light speed, severs that connection. You leave Earth knowing that the journey is one way in a psychological sense, that even if you physically return, years will have passed, people will have aged, the world will have changed. You become a traveller in time as well as space, moving forward through years while covering distance. And what would you find when you arrived? Proxima Centauri has planets. One of them, Proxima Centauri b, orbits in the habitable zone where liquid water could theoretically exist. But we know almost nothing about it. We do not know if it has an atmosphere, if it has water, if it is geologically active, if it has magnetic fields to protect it from stellar radiation. We have observed it only through the tiny wobble it induces in its star's motion and the slight dimming when it passes in front of the star. We have never seen its surface. We do not know what you would encounter there. You would be travelling to a destination about which almost everything is unknown, committing 5 months of your life to reach a place that might be barren, hostile, or uninhabitable. This is the human meaning of faster-than-light travel. It is not the opening of the galaxy. It is the extension of human reach by a few light years, enough to visit the nearest neighbours, enough to turn a handful of stars from abstract points of light into real destinations, but not enough to make the universe accessible. It is progress measured in the smallest units against a scale that remains incomprehensibly large. It is the difference between being confined to one planet and being able to visit a few dozen stars within a lifetime. The universe contains hundreds of billions of stars in our galaxy alone, and hundreds of billions of galaxies beyond. 10 times light speed reaches an infinitesimal fraction of that vastness. And yet it would mean something. It would mean that Earth is not a prison, that the solar system is not the absolute boundary of human presence. It would mean that humans could become a multi-star species, that life originating on Earth could spread to other worlds, that the experiment of consciousness and civilization could be replicated in multiple locations, reducing the risk that a single catastrophe could end it permanently. It would mean that questions about other life, about other planets, about the conditions that produce complexity and awareness. But it would not make space less hostile. It would not make distances less vast. It would not change the fact that humans are fragile biological organisms adapted to a narrow range of conditions that exist only on one planet in the entire observable universe. Travelling faster than light would allow humans to reach other stars, but surviving there, thriving there, building something lasting there, those challenges would remain as difficult as they have always been. Speed solves the problem of distance. It does not solve the problem of survival. This is what faster than light travel would mean for humans. It would transform the nearest stars from unreachable to barely reachable. It would change interstellar travel from impossible to extraordinarily difficult. It would open a narrow corridor into the galaxy while leaving most of the universe as distant as it has always been. And it would do all of this only if the theoretical barriers can be overcome, only if exotic matter can be created, only if the energy can be supplied, only if causality can be preserved. The meaning is real, but it is modest. It is not the conquest of space. It is the first tentative step beyond the solar system, a step that would take everything humans have learned about physics, engineering and survival, and even then might not be enough. In 1994, a physicist named Miguel Alcubierre published a paper that changed how scientists thought about faster-than-light travel. The paper was short, technical, and carefully worded. It did not claim to have invented a warp drive or to have solved the problem of interstellar travel. It claimed something more modest and more profound. It showed that the equations of general relativity, the equations that describe how mass and energy curve spacetime, permit a solution where a spacecraft could travel faster than light without violating the local speed limit. The solution was mathematically rigorous. It satisfied Einstein's field equations, and it revealed a loophole in the structure of spacetime that no one had previously described in such explicit detail. The Alcubierre metric, as the solution came to be known, describes a bubble of curved spacetime that moves through flat background space. Inside the bubble, spacetime is flat. A spacecraft sitting at the center experiences no acceleration, no tidal forces, no time dilation. From the perspective of anyone inside, they are at rest, floating in a region of ordinary unwarped spacetime. But outside the bubble, space is anything but flat. Ahead of the bubble, space contracts. Distances shrink. Points that were far apart come closer together. Behind the bubble, space expands. Distances grow. Points that were close move farther apart. The bubble itself rides this wave of contraction and expansion, moving through space at speeds that can exceed light from the perspective of an outside observer. The key insight is that the spacecraft never moves through space faster than light. It remains at rest relative to the space immediately around it, sitting motionless inside the flat region at the center of the bubble. What moves is the bubble itself, and the bubble is not an object moving through space. It is a configuration of spacetime, a geometric distortion that propagates through the universe. There is no speed limit on how fast spacetime can expand or contract, only on how fast objects can move through spacetime. The distinction is subtle but essential. The Alcubierre drive does not propel the spacecraft. It propels the space around the spacecraft, carrying the spacecraft along without ever requiring it to accelerate. To understand the geometry, imagine a two-dimensional analogy. Picture a flat rubber sheet stretched tight. Place a coin on the sheet to represent the spacecraft. Now imagine gripping the sheet ahead of the coin and pulling it toward the coin, bunching it up so that distant points on the sheet are brought closer. Simultaneously, grip the sheet behind the coin and stretch it, pushing distant points farther away. If you move the bunched and stretched regions smoothly across the sheet, the coin moves with them, carried by the deformation of the sheet itself, never sliding across the rubber. This is the essence of the Alcubierre metric. The spacecraft does not move, the space moves. And because space can move at any speed, the spacecraft can cover arbitrary distances and arbitrary times. The mathematics that describes this geometry is complex but not impenetrable. The metric is written as a modification of flat spacetime, a set of adjustments to the distances and times measured by an observer moving with the bubble. The adjustments depend on a function that determines the shape of the bubble, how steeply space contracts ahead and expands behind, and how large the flat region in the centre is. Alcubierre chose a specific function that produces a smooth transition between the contracted region, the flat region, and the expanded region, avoiding singularities and infinite curvatures. The result is a well-defined geometric object that satisfies the field equations of general relativity. But satisfying the field equations is not the same as being physical. General relativity relates the curvature of spacetime to the distribution of mass and energy that creates that curvature. Given a distribution of mass and energy, you can calculate the curvature. Given a curvature, you can calculate what distribution of mass and energy would produce it. Alcubierre worked backward. He specified the curvature, the geometry of the warp bubble, and then solved for the distribution of mass and energy required to create it. The solution was unambiguous. To produce the Alcubierre metric, you need matter with negative energy density distributed in a thin shell around the spacecraft. This is where the solution transitions from interesting to problematic. Negative energy density is not ordinary matter, it is exotic matter. Matter that violates the energy conditions that all known forms of matter satisfy. The quantity of exotic matter required in Alcubierre's original formulation was enormous, equivalent to the mass energy of Jupiter or more, depending on the size of the bubble and the desired velocity. And this exotic matter must be arranged in a precise configuration, maintained throughout the journey, and somehow prevented from collapsing or dissipating. The solution is mathematically valid, but the requirements make it physically implausible. Despite these obstacles, the Alcubierre metric demonstrated something important. It showed that faster-than-light travel is not absolutely forbidden by general relativity. The theory permits geometries where effective speeds exceed light, where distances can be crossed in time shorter than light would take, where the constraint that nothing moves through space faster than light can be circumvented by moving space itself. This was not previously obvious. Before Alcubierre, most physicists assumed that faster-than-light travel was impossible, full stop, prohibited by the structure of relativity in some fundamental way. The Alcubierre metric proved that assumption wrong. The prohibition is not absolute. It is conditional, dependent on the existence of exotic matter and the ability to manipulate spacetime in ways we cannot currently achieve. The publication of the Alcubierre metric sparked renewed interest in the physics of faster-than-light travel. Researchers began exploring variations of the geometry, looking for modifications that might reduce the exotic matter requirements or eliminate other problematic features. Some found that changing the shape of the bubble, making it thicker in some dimensions and thinner in others, could reduce the energy requirement significantly. Others investigated whether quantum effects might provide alternative mechanisms for creating the necessary spacetime curvature without requiring macroscopic exotic matter. Still others examined the causal structure of the Alcubierre spacetime, checking whether the geometry permits closed time-like curves or other pathologies that would make it unphysical. One significant concern is the horizon problem. Inside the Alcubierre bubble, the spacecraft is causally disconnected from the region ahead. Light from objects in front cannot reach the spacecraft because the space between them is contracting faster than light can traverse it. This means the passengers cannot see where they're going. They cannot detect obstacles, navigate around hazards, or even confirm that the bubble is still moving in the intended direction. The spacecraft is effectively travelling blind, committed to a trajectory determined when the bubble was formed, with no ability to adjust course based on new information. This is not merely inconvenient, it is potentially catastrophic if the trajectory intersects any significant mass. Another concern is energy accumulation. As the bubble moves, it interacts with particles and radiation in the surrounding space. These interactions deposit energy at the boundary of the bubble, particularly at the leading edge where space is contracting. Over the course of a long journey, the accumulated energy could become substantial, possibly even comparable to the energy required to create the bubble in the first place. When the bubble is dissolved and the spacecraft returns to normal spacetime, this energy must be released. Some calculations suggest it would be released as a burst of high-energy radiation directed forward, potentially energetic enough to destroy anything in its path. The warp drive might function, but stopping it safely could be as difficult as starting it. These issues have not been resolved. They remain open questions in the theoretical study of the Alcubierre metric. Some physicists believe they indicate fundamental problems with the concept, signs that the geometry, while mathematically valid, is not physically realizable. Others believe they are challenges that might be addressed with further refinements, additional constraints, or deeper understanding of quantum gravity. The Alcubierre solution exists. It is a real solution to the equations of general relativity, but whether it describes anything that could exist in the physical universe remains uncertain. What the Alcubierre metric accomplished was to shift the conversation. Before 1994, faster-than-light travel was largely the domain of science fiction, dismissed by physicists as inconsistent with relativity. After Alcubierre, it became a topic of serious inquiry, a problem with mathematical structure and physical constraints that could be studied rigorously. The solution is almost certainly not practical. It may not even be possible. But it demonstrated that the universe is stranger than simple intuition suggests, that space-time is more flexible than everyday experience reveals, and that the boundary between impossible and merely extraordinarily difficult is not always where you expect it to be. The problem with the Alcubierre metric, from the moment it was published, was not that it violated the equations of general relativity. The problem was the cost. The exotic matter requirements were so extreme, the energy density so far beyond anything achievable, that the solution felt more like a mathematical curiosity than a blueprint for technology. For decades, the metric existed as proof that faster-than-light travel was theoretically permissible, but practically absurd. Then, in recent years, physicists began finding ways to reduce the requirements, not eliminate them, not make them achievable with current technology, but reduce them enough that the gap between theory and possibility narrowed, enough that the conversation shifted from impossible to extraordinarily difficult. The first major refinement came from reconsidering the shape of the warp bubble. Alcubierre's original design was relatively symmetric, a smooth distribution of contracted and expanded space surrounding a flat central region. But symmetry is not required. The equations of general relativity do not demand that the bubble be spherical, or that the curvature be uniform in all directions. By flattening the bubble, making it wider in some dimensions and narrower in others, researchers found they could achieve the same effective velocity with significantly less exotic matter. The total energy requirement dropped from the mass energy equivalent of Jupiter to something closer to the mass energy equivalent of a large asteroid, or even a massive spacecraft. This is still enormous, still far beyond any energy source humans have ever built, but it is several orders of magnitude smaller than the original estimate. The key insight was that not all parts of the bubble contribute equally to the net motion. The contraction ahead and expansion behind need to be strong enough to produce the desired velocity, but they do not need to be symmetric. A flattened bubble, more like a disk than a sphere, can achieve the same result with less total curvature, and less curvature means less exotic matter. The trade-off is that the bubble becomes more fragile, more sensitive to perturbations, and potentially more difficult to stabilize. But the energy savings are substantial enough that flattened geometries became the focus of subsequent research. Another refinement involved the thickness of the warp bubble's walls. In Alcubierre's original formulation, the transition between the contracted region, the flat region, and the expanded region occurs over a relatively thin shell. The thinner the shell, the steeper the curvature, and the more exotic matter required to produce it. By making the transition more gradual, spreading the curvature over a thicker region, the energy density at any given point decreases. The total amount of exotic matter may remain similar, but it is distributed more diffusely, which may make it easier to generate and control. Again, the improvements are incremental, the requirements remain extreme, but the direction of change is encouraging. Each refinement makes the concept slightly less impossible. In 2021, a team of researchers proposed a modification that reduced the energy requirements even further by introducing a different class of spacetime geometries. Instead of a bubble that moves through flat background space, they considered bubbles that exploit the natural curvature of spacetime around massive objects. Near a star or planet, spacetime is already curved by the mass present. If you can create a warp bubble in a region that is already curved, you might be able to use that existing curvature to reduce the additional curvature needed from exotic matter. The bubble would effectively borrow some of its geometry from the gravitational field, reducing the burden on the exotic matter. The savings are modest, and the approach introduces complications related to navigating through curved regions, but it represents another incremental step toward feasibility. More recent work has focused on the question of whether exotic matter is truly necessary. Some physicists have explored whether quantum effects, particularly effects related to the vacuum energy of fields, might provide alternative mechanisms for warping spacetime without requiring macroscopic negative energy densities. The Casimir effect demonstrates that quantum fields can produce forces and energy distributions that differ from classical expectations. If these effects could be scaled up or harnessed in specific configurations, they might generate the curvature needed for a warp bubble without violating energy conditions as severely as Alcubierre's original design requires. This remains highly speculative. No one has demonstrated that quantum vacuum effects can be controlled at the scales necessary for a warp drive, but the possibility has opened new avenues for research. There have also been proposals to reduce the velocity requirements by accepting longer travel times. If you do not need to travel at 10 times the speed of light, if you are willing to accept 1 or 2 times the speed of light, the exotic matter requirements drop dramatically. At velocities just barely exceeding light speed, the curvature needed is much gentler, the energy density is much smaller, and the stability concerns much less severe. A warp drive capable of reaching 1.1 times light speed would still represent a revolutionary advance, making journeys to nearby stars feasible within human lifetimes, even if not as quickly as more dramatic velocities would allow. The trade-off between speed and feasibility is another dimension of the problem that researchers are exploring. All of these refinements share a common feature. They reduce the requirements, but they do not eliminate them. They make the warp drive less impossible, but they do not make it possible. The most optimized geometries still require exotic matter. They still require energy densities that have never been observed. They still require technologies that do not exist and may never exist. The gap has narrowed, but it remains a gap. The distance between a solution that works on paper and a solution that works in reality has decreased, but it has not closed. And even if all the technical obstacles were overcome, even if exotic matter could be created and controlled, even if the energy could be supplied and the bubble stabilized, there remain unanswered questions about what would happen when you actually used the device. Would the bubble remain stable over interstellar distances? Would interactions with interstellar gas and dust destabilize it? Would gravitational fields from stars and planets disrupt the geometry? Would quantum fluctuations in the vacuum perturb the exotic matter distribution? These are questions that cannot be answered theoretically. They would require experiments, observations, data from actual warp bubbles, and we are nowhere near being able to create those. The refinements are progress. They demonstrate that the problem is being taken seriously, that physicists are not content to dismiss the Alcubierre metric as a mathematical toy, but are actively exploring whether some version of it might be realizable. They show that the energy requirements, while still extreme, are not as insurmountable as they first appeared. They reveal that spacetime is more flexible than initial estimates suggested, that there are multiple ways to achieve similar geometries, and that optimization is possible even in regimes where the physics is exotic and unfamiliar. But they also underscore how far we are from practical faster-than-light travel. Every refinement that reduces the exotic matter requirement by an order of magnitude still leaves requirements that are orders of magnitude beyond what we can achieve. Every optimization that makes the bubble more stable still leaves a system that is inherently unstable compared to ordinary matter. Every improvement that broadens the range of possible geometries still operates within constraints that may ultimately prove insurmountable. The refinements are real, the progress is real, but the gap between theory and practice remains vast, and there is no clear path from where we are to where we would need to be. This is the state of the research. Scientists have revealed methods to reduce the requirements for faster-than-light travel. They have found geometries that are less extreme, less demanding, less absurd than the original Alcubierre metric. They have shown that the problem is not static, that understanding deepens, that constraints can be relaxed through careful analysis and creative thinking. But they have not shown that faster-than-light travel is achievable. They have not demonstrated that exotic matter can be created. They have not proven that the refined geometries are any more physical than the original. They have revealed a method, but the method remains theoretical, a description of what might be possible if conditions that do not exist could somehow be brought into being. There is a difference between what equations permit and what reality allows. This distinction is easy to forget when reading about theoretical breakthroughs, when headlines announce that scientists have found a way to travel faster than light, when the language suggests that a solution has been discovered and implementation is merely a matter of engineering. But the distinction is fundamental. Mathematics can describe worlds that do not exist. Equations can have solutions that correspond to nothing real. And the fact that a geometry satisfies Einstein's field equations does not mean that geometry can be created in the physical universe. The Alcubierre metric and all its refinements remain solutions to equations. They are descriptions of how spacetime would need to curve to produce faster-than-light travel, specifications of what distribution of mass and energy would create that curvature. But they are not instructions for building anything. They are not blueprints that can be handed to engineers. They are theoretical constructs that reveal possibilities within the mathematical framework of general relativity, while remaining disconnected from physical reality in ways that may be insurmountable. Consider exotic matter. Every version of the warp drive requires it. Every refinement reduces the quantity needed but does not eliminate the requirement. And exotic matter in the forms and quantities required has never been observed. The Casimir effect produces infinitesimal amounts of negative energy over microscopic distances. Quantum field theory permits temporary, localized violations of positive energy density. But scaling these effects up to the macroscopic level, creating enough negative energy to warp spacetime around a spacecraft and maintaining it for the duration of an interstellar journey, is not simply a matter of building better equipment or discovering new techniques. It may be fundamentally prohibited by principles we do not yet fully understand. Quantum energy inequalities place limits on negative energy. These inequalities are not arbitrary constraints imposed by cautious physicists. They emerge from the structure of quantum field theory, from the requirement that fields obey causality and that the vacuum remains stable. They state that the more negative energy you want, the shorter the time it can exist and the smaller the region it can occupy. The relationship is inverse and strict. Large amounts of negative energy over large volumes for long durations appear to be forbidden, not by current technology, but by the laws governing quantum fields, and the warp drive requires precisely this. Large amounts of negative energy distributed over volumes measured in meters or kilometers, sustained for months or years. If quantum energy inequalities are correct, and all evidence suggests they are, then the warp drive is impossible, not difficult, not awaiting future breakthroughs. Impossible in the same sense that perpetual motion machines are impossible, ruled out by fundamental principles that cannot be circumvented through cleverness or technology. The equations of general relativity permit the geometry, but the equations of quantum field theory may prohibit the matter needed to create that geometry. The two theories, general relativity and quantum field theory, do not yet merge into a unified theory of quantum gravity, and their boundary is precisely where the warp drive sits, requiring features from both theories that may be incompatible when fully understood. Even if exotic matter could be created, there is no known mechanism for controlling it. Negative energy densities are unstable. They want to decay, to radiate, to equalize with the surrounding vacuum. Preventing this would require some form of containment, some field or force that holds the exotic matter in its required configuration. But what force? Electromagnetic fields cannot confine exotic matter, because exotic matter, by definition, has unusual properties that ordinary matter does not. Gravitational fields are too weak to provide the necessary confinement at the scales involved. Strong and weak nuclear forces operate only at subatomic distances. There is no known interaction that could stabilize macroscopic quantities of exotic matter against decay. You might propose new physics, new fields or particles or interactions that provide the necessary stability. But this is speculation layered on speculation. You're not only assuming that exotic matter can be created, which itself has no experimental basis, but also assuming that entirely new physics exists to control it, physics that has never been observed and for which there is no evidence. At some point, the stack of assumptions becomes so high that the proposal stops being science and becomes wishful thinking, a narrative constructed from mathematical possibilities without connection to physical reality. There is also the energy problem, which refinements have reduced but not eliminated. Even the most optimized warp bubble geometries require energy equivalent to the mass of a large spacecraft or asteroid, converted entirely into exotic matter. This is not energy in the sense of fuel that can be burned or batteries that can be charged. This is rest mass energy, E equals mc squared, the energy locked in matter itself. To convert mass into energy at this scale requires processes like matter-antimatter annihilation, which occurs with perfect efficiency, but requires equal amounts of matter and antimatter. Producing and storing antimatter in the quantities needed is itself a monumental challenge, far beyond current capabilities, and even if you could produce it, converting it into exotic matter rather than ordinary energy is not a process that has ever been demonstrated or even proposed in concrete terms. The causality problem remains unresolved. Faster-than-light travel, combined with the relativity of simultaneity, permits scenarios where effects precede causes. You can construct thought experiments where messages arrive before they are sent, where timelines loop back on themselves, where logical contradictions become inevitable. Some physicists argue that additional constraints must exist, hidden principles that prevent these paradoxes even when the geometry permits them. Others argue that the paradoxes themselves are evidence that the geometry is unphysical, that the universe does not allow configurations that would break causality. No consensus has emerged. The problem sits at the intersection of general relativity and quantum mechanics, in a regime where neither theory alone provides definitive answers, and then there are the practical unknowns. Suppose all the theoretical obstacles were overcome. Suppose exotic matter could be created, controlled, and sustained. Suppose the energy could be supplied. Suppose causality paradoxes could be avoided through some mechanism we do not yet understand. You would still be attempting something that has never been done, creating a macroscopic distortion in spacetime, a travelling wave of curvature propagating through the universe at speeds exceeding light. What would happen? Would the bubble remain stable? Would quantum fluctuations destabilize it? Would interactions with the cosmic microwave background, with interstellar gas, with gravitational fields from distant stars perturb the geometry? These are questions that cannot be answered without experiments, and experiments are impossible when the phenomenon requires resources that do not exist. This is why the warp drive remains impossible. Not impossible in the sense that we currently lack the technology. Impossible in the sense that every step toward making it real encounters obstacles that are not technical but fundamental. Exotic matter may be forbidden by quantum field theory. The energy requirements may be unpayable even by advanced civilizations. Causality may impose constraints that prevent faster-than-light travel regardless of the geometry. And the unknowns are so vast that even identifying all the problems is beyond current physics. When scientists say they have revealed a method to travel faster than light, they are speaking precisely and carefully. They have revealed a method in the sense that they have described a geometry, a configuration of spacetime that would produce the desired effect if it could be created. But revealing a method is not the same as demonstrating feasibility. It is not the same as showing a path from theory to practice. It is not the same as proving that the universe permits what the equations describe. The method exists on paper, it does not exist in reality, and the gap between those two may be unbridgeable. The refinements are genuine progress in understanding the theoretical space of possibilities. They show that the problem has structure, that some solutions are less extreme than others, that optimization is possible within the constraints of general relativity, but they do not change the fundamental conclusion. The warp drive is a mathematical solution that describes something the physical universe probably does not allow. It is a proof that faster-than-light travel is not absolutely forbidden by the geometry of spacetime, but it is also a demonstration of how many other barriers stand between theoretical possibility and physical realization. The method has been revealed. The method remains impossible. Even if the warp drive worked, even if every obstacle were overcome and faster-than-light travel became possible, the universe would remain vast. This is the conclusion that emerges when you step back from the equations and the energy requirements and the exotic matter debates, and consider what faster-than-light travel would actually change. It would change travel times to nearby stars. It would make a handful of stellar systems accessible within human lifetimes, but it would not shrink the universe. It would not make distances irrelevant. It would not transform the cosmos into something humans could traverse, casually, or comprehend fully. The scale would remain overwhelming, the distances would remain extreme, and the vast majority of the universe would remain as unreachable as it has always been. 10 times the speed of light allows you to reach Proxima Centauri in 5 months. It allows you to reach a dozen nearby stars within a year or two. These are genuine achievements. They represent the difference between stars that are theoretical destinations and stars that are places humans could actually visit. But 10 times light speed does not allow you to explore the galaxy. The Milky Way is 100,000 light-years across. At 10 times light speed, crossing it would take 10,000 years. 10,000 years is longer than all of recorded human history. It is longer than human civilization has existed. It is a timescale on which species evolve, on which continents drift, on which ice ages come and go. Even with faster-than-light travel, the galaxy remains too large for comprehensive exploration. Consider the nearest significant concentration of stars, the galactic core, where hundreds of billions of stars cluster within a relatively small volume. The core is 26,000 light-years away. At 10 times light speed, 2,600 years to reach it. By the time you arrived, the civilization that sent you would be unrecognizable. Languages would have changed. Nations would have risen and fallen. Technologies would have advanced in ways impossible to predict. You would return to a world that bears no resemblance to the one you left, if you returned at all. The distance is reduced in time, but it is not reduced in significance. The journey remains one that severs you from your origin, that makes return meaningless because the place you left no longer exists, and the galactic core is nearby compared to most of the galaxy. The outer spiral arms, the regions where new stars form and where conditions might favour the development of life, are tens of thousands of light-years away in every direction. The nearby dwarf galaxies, small satellite galaxies orbiting the Milky Way, are hundreds of thousands of light-years away. Andromeda, the nearest large galaxy, is 2.5 million light-years away, 250,000 years at 10 times light speed. These are not distances that can be crossed within any framework that preserves continuity with human civilization. They are distances that require generations, that require accepting that the travellers will never return, that require building societies capable of sustaining themselves for timescales longer than nations have ever existed. Even 100 times the speed of light, even 1,000 times, would not fundamentally change this picture. At 100 times light speed, the galactic core is 260 years away, still multiple human lifetimes. At 1,000 times light speed, 26 years, within a single lifetime but barely. And 1,000 times light speed is not what the refined warp drive geometries propose. The optimizations reduce energy requirements at modest velocities. Achieving speeds 1,000 times faster than light would require exotic matter and energy densities far beyond even the most optimistic refinements. The faster you want to go, the more extreme the curvature must be, and the more impossible the requirements become. The universe is structured in layers of scale, each layer separated from the next by factors of thousands or millions. You can reach the moon in days with chemical rockets. You can reach Mars in months. You can reach the outer planets in years or decades using gravitational assists and efficient trajectories. These are scales where human intuition still functions, where missions can be planned and executed within careers, where results can be seen by the people who initiated the projects. But beyond the solar system, the scales explode. The nearest star is tens of thousands of times farther than the outer planets. The galaxy is millions of times larger than the distance to the nearest star. The observable universe is billions of times larger than the galaxy. Each jump in scale increases the distance by factors so large that even dramatic improvements in speed barely matter. Faster-than-light travel addresses the first jump from the solar system to nearby stars. It turns a journey that would take tens of thousands of years into one that takes months. This is transformative at that scale. But it does nothing for the subsequent jumps. The galaxy remains immense. The universe remains incomprehensible. Travelling 10 times faster than light is like upgrading from walking to driving, in a world where most destinations are on other continents. The improvement is real, but the distances that matter remain far beyond what the improvement allows. This is not a pessimistic view. It is a realistic assessment of what scales mean. The universe is not built for easy traversal. The distances between interesting places are measured in years, even at light speed, in decades or centuries, even at 10 times light speed. the arrangement of matter and energy across these distances is sparse. Most of space is empty. Most stars are isolated. Most galaxies are separated by voids that contain almost nothing. The universe is structured to keep things apart, to maintain isolation, to prevent easy interaction across large scales. Faster-than-light travel reduces some of this isolation, but it does not eliminate it. It does not change the fundamental fact that the universe is mostly distance, mostly separation, mostly empty space across which even the fastest possible travel takes lifetimes. There is also the question of what you would do if you could reach distant places. Stars are not destinations in the way cities or countries are destinations. A star is a ball of plasma undergoing fusion, radiating energy, creating a hostile environment for anything not adapted to extreme heat and radiation. The destinations are planets, moons, asteroids, places where humans might land, explore, build. But planets are small compared to the distances between stars. Even if you travel faster than light to reach a star system, you still need to slow down, survey the system, identify which bodies are worth visiting, travel within the system using slower propulsion, and survive in environments that are almost certainly hostile. The warp drive, if it existed, would get you to the star system. It would not solve the problems of exploration, survival, or colonization once you arrived. And each journey would be unique, unrepeatable in certain ways, because traveling faster than light requires exotic matter that must be created, configured, and maintained for each trip. If the energy cost is equivalent to a large spacecraft or asteroid, then each journey consumes resources on a scale that makes frequent travel impossible. You would not take shortcuts to nearby stars casually. You would plan each journey carefully, allocate resources deliberately, accept that each departure is an event of enormous significance. Faster-than-light travel would not be routine. It would remain extraordinary, expensive, and rare, reserved for missions of exploration or settlement, not for casual transit or tourism. The universe is large. This is a simple fact, but its implications are profound. Large means that distance matters more than speed. Large means that even dramatic increases in velocity produce modest reductions in travel time when measured against cosmic scales. Large means that the vast majority of the universe remains inaccessible, no matter what technology you develop, because the distances are so extreme that even light, traveling for billions of years, has not reached us from the most distant regions. Faster-than-light travel changes the accessible region from a sphere a few light years in radius to a sphere a few dozen light years in radius. This is an increase. It is not a transformation. When scientists reveal a method to travel 10 times faster than light, they are revealing a method that addresses the nearest layer of distance. They are not revealing a method that conquers distance itself. The universe remains large, the stars remain far apart, the galaxies remain isolated, and even the most optimistic scenarios for faster-than-light travel leave most of the cosmos beyond reach, existing as light we can see but places we can never visit, structures we can observe but never touch. The method has been revealed. The distance remains unchanged. You began this journey with a phrase, 10 times faster than light. It sounded like progress, like a boundary being crossed, like humanity approaching something that was once forbidden. And in a sense, it is progress. Physicists have described geometries of spacetime that permit motion at speeds exceeding light, have refined those geometries to reduce their requirements, have shown that the equations of general relativity contain possibilities that were not obvious when Einstein first wrote them down. This is genuine understanding, genuine expansion of what we know the universe might allow. But understanding what equations permit is not the same as achieving what reality allows. The warp drive exists as a solution on paper, a configuration of spacetime that satisfies the mathematics of general relativity, while requiring matter that has never been observed and energy that has never been harnessed. The refinements are real. The reductions in exotic matter requirements are substantial, but they reduce the impossible to the extraordinarily difficult, and the extraordinarily difficult remains out of reach. Exotic matter may be forbidden by quantum field theory. The energy costs may be unpayable. Causality may impose constraints that prevent faster-than-light travel regardless of geometry. The method has been revealed, but the method remains theoretical, and even if it were not, even if every obstacle could be overcome, the universe would remain vast. 10 times the speed of light makes nearby stars accessible. It turns journeys measured in tens of thousands of years into journeys measured in months. But it does not shrink the galaxy. It does not make distant regions reachable. It does not change the fundamental fact that the universe is built on scales that exceed human lifetimes by factors of millions, scales where even light takes billions of years to cross from one edge to the other. Faster than light travel addresses the nearest layer of distance. It does not conquer distance itself. This is not a story about a breakthrough. It is a story about limits. The speed of a light is not an arbitrary speed limit that clever engineering might bypass. It is a property of space-time, a feature of how reality is structured at its most fundamental level. When light moves, it connects events in a way that preserves causality, that ensures cause precedes effect, that maintains the logical sequence of time. The speed at which light moves is the speed at which information can propagate, the speed at which one part of the universe can influence another, the speed at which reality itself operates. You live in a universe where light takes 8 minutes to travel from the sun to Earth, where light from the nearest star takes 4 years, where light from distant galaxies takes billions of years. These are not inconvenient delays. They are expressions of the structure of space-time, reflections of how far apart things truly are when measured in the only currency that matters, the time it takes for influence to propagate, for signals to cross, for one location to affect another. The universe is large because space-time is structured to keep events separated, to maintain causal order, to prevent the kind of instantaneous action at a distance that would make time meaningless. The warp drive, if it could exist, would not violate this structure. It would exploit a loophole, a geometric possibility where space itself moves while objects within it remain stationary relative to their local surroundings. The spacecraft would not travel faster than light through space. Space would travel, carrying the spacecraft with it, and space can move at any speed because there is no speed limit on geometry. But this loophole requires bending space-time so severely, concentrating exotic matter so precisely, and maintaining the configuration so stably that it may be forever beyond reach. The loophole exists in theory, it may not exist in practice. And so you are left with the speed you have. Light moves at 186,000 miles per second. This is fast by human standards, incomprehensibly fast compared to cars or airplanes or anything you have direct experience with, but it is slow compared to the universe. At this speed, the nearest stars are years away. The galaxy is tens of thousands of years across. The observable universe is billions of years from edge to edge. These distances are not obstacles to overcome. They are features of the universe, aspects of its structure that cannot be eliminated through technology or determination. Humans have reached speeds of 430,000 miles per hour, less than 1/10 of 1% of light speed. This is the fastest speed ever achieved by any object humans have built. It is extraordinary by the standards of a species that evolved to walk at a few miles per hour, but it is negligible by the standards of interstellar distance. At this speed, the stars remain unreachable. The galaxy remains closed, the universe remains immense and mostly empty, filled with light from distant places that will never be destinations, only observations. This is what it means to exist in a universe governed by the speed of light. You are confined to a small region of space, a bubble around your origin point that expands slowly as technology improves, but never fast enough to encompass more than a tiny fraction of what exists. You can see farther than you can travel. You can observe galaxies you can never visit. You can detect light from the early universe, light that has been travelling for 13 billion years, crossing distances so vast that even at 10 times the speed of light you could not reach its source within the lifetime of the universe itself. The revelation that faster than light travel might theoretically be possible does not change this. It shows that the universe is more flexible than simple intuition suggests, that space-time can be warped in ways that create surprising possibilities. But possibilities on paper are not possibilities in reality. The distance between mathematical solution and physical device is as large as the distance between stars, and there is no clear path across it. The method has been revealed. The method remains inaccessible. You are left with wonder, with the knowledge that the universe is stranger than it appears, with the understanding that the barriers you face are not arbitrary but fundamental. The speed of light is the speed of causality, the speed at which the universe operates. is not fast enough to make the cosmos traversable, but it is the speed you have. And it is the speed that connects you to everything you can see, every photon that reaches your eye carrying information about distant places, every signal that crosses space bringing news of stars and galaxies and the structure of reality itself. The universe is vast. It will remain vast, and you will remain small, contained within a region measured in light years, looking outward at distances measured in billions, understanding that the gap between here and there is not a gap that technology can close, but a gap that defines what it means to exist in space-time. The speed we have is the speed we will always have, and the universe, indifferent to ambition, continues to expand, continues to separate, continues to exist on scales that exceed all human attempts to traverse it. This is the speed we have. This is the universe we inhabit. And this is what it means when scientists reveal a method to travel faster than light. They reveal a loophole that cannot be used, a possibility that cannot be realized, a solution that describes nothing real. The universe remains as it has always been, vast, distant, and governed by a speed that is both impossibly fast and impossibly slow, depending on what you're trying to reach.